give you, tell you that you have a vibrating system that has an equation, maybe 2x prime prime plus, plus 7x equal to 0, okay? Where x of 0 is equal to 1 and x dot of 0 equal to 0. That's it. And if I tell you, if you have the vibrating system like this, what is the frequency of vibration?
Now look at what I just did
What?
on my lab report.
Now,
Should we know the answer out of,
Yep.
you should, without looking at anything, you should know what the answer is.
Okay.
7/2?
Square root.
Good guess.
Pretty close.
I like it, Chris, I like it.
Pretty close. Now, whenever
Square
you
root
get
of
questions like
K over-
this, okay, how would you describe this vibrating system? First of all, you go like, what, you know, vibrating system typically contains what? What components?
Mass spring damper.
Mass cream damper. What do you think is, what do you think our vibrating system contains based on this equation?
The mass of the spring, but no damper.
Exactly. What is the mass equal to?
2?
Yes, and what is the spring equal to? Spring constant?
7.
7. Why are you saying this? Because you always have to model it by,
That's right.
that's your rule of thumb, right? Whenever you look at the equation, always try to adapt it to this. And what did we say was the natural frequency?
Square root of K over.
K over M, which is square root of,
7.
there you go, done. Radians per second, okay?
What is WN again? Like,
Natural frequency.
natural frequency.
Natural frequency is when you.
I was
release.
close, I just forgot the root.
That's why I told you earlier you were close.
I
You just
thought it, but I
forget the-
didn't say it.
You just forget the square root. So always try to take the equation and, you know, this is too dry. It's just an equation, right? A mathematician is not gonna think this is a mass, nor is he gonna think this is a damper. He's just gonna say, what's a second order differential equation? Let me solve it. That's what he would do, you know, write the characteristic equation and find omega from there is gonna tell you that. But we engineers, we try to look at that and say, hey, this is the equation of a mass spring damper, right? Where the mass is 2, the damper is, or the spring constant is 7, and you go on, okay? And if I were to give you something like this and would say, okay, can you tell me how x varies as a function of t? What would you do?
Initial condition.
Well, let me tell you that, well, you're gonna have, you know that this is a sinusoidal thing, right?
Okay.
So you're gonna say maybe one of you would say, well, I'm just gonna write it as a sine omega n t plus t. You know, somebody may use cosine, right? Who cares, right?
Does it matter?
It doesn't matter.
Whatever direction.
Whatever, as long as it's a
Oh, right.
harmonic,
Right, okay.
right? But what is our goal here now is to find out. You can't just say it's a sine omega t, because omega n, you already told me what it is. But what is, you need to figure out what is a and what is v. And how do you do those?
Initial.
Initial conditions, okay? So what is x of 0 equal to? It's 1, so it's 1, but by virtue of this equation, it is what? A sine of
5.
phi of v, okay? And then you go like, x dot. What is x dot in here? Equal to.
You have to do the chain rule? Yeah.
A sine, sorry, A cosine,
A cosine,
omega n t plus phi, and then times omega n.
It's minus
It's not,
cosine.
this is
Times
derivative
omega.
cosine is negative sine.
are we good here? Okay, so what's x dot 0 equal to? 0, and this is equal to?
A omega n cosine phi.
Cosine phi. Right, 0 equals A omega n cosine phi. Now, how do I solve this? This is not telling me, I need to know what A
Don't
is.
you have to put the,
You need
the
two
square root
equations.
Square root,
of 7/2?
that would be,
That's
That's
You
all.
know what
Yeah.
it is, right?
we know what it is, so
Yeah, we
we'll
don't
just
have to
keep
do
it
it
like
Yeah, we're
that.
not, we're not solving for that.
So how do you solve for phi here?
Oh, you do,
Like the
you
arctangent.
add our.
What is that?
What if you divide the equation and get a tangent?
Exactly. Anytime you have sine and cosine, it's more likely that you have to take it so that you get a tangent equal to something, right?
Yeah.
So if I divide this equation by this equation, what do I get? 1 divided by 0 equals what?
0. No,
One
1.
divided by 0.
1 divided by nothing is 1,
That's
right?
infinite.
You can't have
And then
tangents.
you can't- no, you gotta get the other way, so you
Yeah.
gotta put a tangent.
Well, 1 divided by 0, technically, you know, your math thinking,
That's
it's
infinite.
infinity, right?
Mm.
Because it's 1 over epsilon, something that's really tiny, tiny, tiny. I mean, in reality, you cannot divide by 0, but we know what we mean, right? So it's
Okay.
plus infinity,
Okay.
A and A
That's one.
cancels out, and then you get tangent phi. So what is tangent phi? So what is the arctangent of
What did you do with omega
infinity
n?
equal
Yeah.
to?
What happened to omega?
Omega, there's omega n, right?
Thank you, yes. What am I talking about?
Should be
This,
over-
it's
over-
1 over omega n?
Right.
Yeah, but what if you divide that by infinity, then you get rid of it.
So if this is infinity, that means that tangent phi technically is infinity, right? I multiply both sides by omega n,
Yeah.
you know, use your head. Multiply both sides by, what's omega n times infinity?
Infinity.
Just infinity is equal to tangent phi. So what is the arctangent of infinity? You guys remember the trigonometric circle? Trigonometric circle looks like this. It has a radius 1, right? This sine, this axis is what? The cosine
Cosine.
axis.
And
This
sine.
sine is the sine axis. And this one is the
Tangent.
tangent axis, right? The other one is the cotangent, but forget about that, right? So, for this, if this is 45 degrees,
Root 2 over 2.
so this is the tangent of 45 degrees, right? When the angle is 0, it is 0. What happens when this angle goes to pi over 2? Where does it tend to
Infinity.
cross that? At infinity, right? So arctangent of plus infinity is equal to pi over 2. Because as you rotate this guy, right, it's going to go higher and higher and higher, and that's the tangent axis.
Okay. Hmm.
Yeah, never
Yeah.
seen this before?
No.
I mean, I'm sure I have.
Yeah.
Not ringing any bells.
Oh, really?
4 years ago.
Wow.
You got the letter, we're screwed.
And it doesn't ring a bell when you say this is the cosine of the angle?
Wait,
Well, that.
Yeah.
Yeah, we know that
I
part.
know that.
And this one is the sine, oh, so
Yeah, but-
nobody told you about the tangent?
No.
No, the
Well,
tangent
they
of,
probably did it.
no, the
Tangent of
tangent of
infinity.
infinity.
Yeah.
Oh, really?
It's in trig, so if you didn't.
But it,
Yeah, I mean, that was
it
so
makes
long ago.
mathematical sense that as you keep going,
You
that-
keep going, it becomes
Some people
parallel.
didn't have to
with
take
your-
it.
Because
I like the trick, but I didn't get it.
Well, I'm glad that we.
Doesn't matter.
Because
yeah, cause it's on the test.
I was going to give something like this on the
Oh,
test, which is an
Jesus.
easy problem, really.
And that's
Yeah.
kind of my struggle with this class, it's just like, okay, I mean, I just don't remember that
Send it
trig
to
identity.
Sophie.
You know, so if I didn't
And
remember
some
that.
of us haven't seen that.
So,
The sign and the, well,
I might have seen it like a long
It makes
time
sense
ago.
when you show
well,
it to
we,
me.
we
Yeah.
solved,
Postponed the
we
test
solved it
for a little
before,
while.
but with not,
Yeah,
it's
not
not
with
infinity.
infinity.
yeah, there's
So
always.
maybe on the
There is a
test,
number.
don't use infinity. let's do that.
Especially that now
Do
that I
something
did it, you're
different.
telling me.
Now that you've done it.
Use this one on the test.
Use this again.
That one, yes.
I think it's too early for a test.
Plus
I think we should
Another week
postpone
or
the
so.
test for a couple
So
weeks.
this is arctangent, so we got pi over two, how about phi? So we got this, right? That means that, this is phi, right? And then to get, what is,
A.
what are we missing? A?
Plug it in.
Maybe we can, maybe we use this one. What's sine of pi over two?
1.
Pi over 2 is
That
1.
means A is equal to
One.
1.
Yeah.
That means that the solution to my equation is simply x of t equals A, which is 1, sine of omega n t plus
Pi over 2.
pi over 2. And by the way, trig identities, sometimes you can, without, you don't have to remember them. If I have an angle, for example, I call this phi, for example, right? And this is the sine, and I want to find the sine of phi over, phi plus pi over 2. Do you agree that this is phi plus pi over 2?
Yes.
Do you agree then that this is the sine of that, of phi over 2? How does it compare to the cosine of phi?
It's the same.
It's the same. So it's a trig identity, you know, which is simply cosine of omega n times t. Trig circle is a lifesaver, you know,
Right on your notes.
don't have to remember.
So
any
trig circle
equations.
should be in our notes, right?
I don't know, I've been using it since I remember, you know. It's-
I would use
It's in
it
your
for
always
spring.
toolbox
It's
because
in
you
my
remember it,
toolbox
yeah.
because I
These
see it.
problems.
My dad taught me when I was a kid, but there's been gaps of using it and not using it. so.
Yeah, okay. So with that said, so there's gonna be, you're gonna have one question like this for sure.
Okay, hold on.
So, just so you know.
I'm taking a picture too, 'cause I don't like
Just
my
so
notes.
you know.
You are.
You're-
Right in the
you're
middle of
blocking
it.
fee.
Oh, my God. All right, let me.
It was
get
better
up.
when you were.
There you go, you're good.
Let me escape then.
Said I could send it to you.
All right,
My head just started hurting.
Just started?
We're only 15 minutes in.
all right, can I erase this now?
Yeah.
Sometime.
Okay.
I have some, I don't have any water.
It started hurting
Yeah.
13 minutes ago.
Okay.
All right, so let's move on with where we stopped last time. We got to this problem and I said, let's do it next time because we were talking on Zoom. I don't know that Zoom thing, very hard. You know, if you don't write things. So this problem here is about, it's an interesting one. You have a spring that's got a mass on top of it, and, right? Well, technically, you have the cantilever beam, which can be modeled as this, where K is equal to 3pi, I believe, over L cubed. And we know where we got this from, you know, the front page of the book, right? Any continuous system can be modeled into this. Now, if you have this, what is the equilibrium position of this guy?
At the bottom.
Somewhere, right? Let's say this or that, but let's just do it at the center line of the mass. We call this maybe YY. So this is equilibrium. This is the static equilibrium, right? Initially. Now, suppose you have a little mass M here at the top, at a height h from the other mass. And I'll call this one H. And technically the H should be the distance from here to here, but you know. What happens when the mass falls from
Which one
the little mass?
pushes the big one down? And
So, yeah, but
It gets
as the
smaller.
mass comes down, eventually what's going to happen?
It's gonna impact that.
It's going to impact, that's the key word, it's going to impact this mass, right?
You're gonna
And then remember in
conservation-
dynamics,
Conservation momentum. is-
conservation of momentum, right?
Mhm.
Conservation of momentum in this direction, right? So what is, first of all, when a mass M falls a certain distance H?
MGH, energy converted to 1/2 times.
It's kinetic.
Okay, so it's MGH equals,
Its final velocity just before it hits would be
1/2 mv squared.
V, so 1/2 mv squared.
okay, so you cancel this guy, right? That gives you V of the little mass M, right? Is equal to
Square root of 2gh.
square root of 2gh, okay? So when this mass gets to here, its velocity downward is equal to Vm equals 2gh squared. Then what happens? There will be impact. And remember in dynamics,
You know, what type of collision is it?
this is the type of collision where the two masses, I believe, were told stay together.
Without rebounding, right?
So-
Do not rebound,
So you're
So
right?
you assume
Inelastic collision.
assume
So it's an
this.
inelastic collision. So,
We lose a
remember,
little bit
if this is our direction, we say, what is the momentum of my little mass is mvm. What is the
Equals
momentum of the big mass?
M plus M, oh, sorry.
What is the initial momentum of this mass?
Zero.
Zero.
Zero, because it's at rest. Because after impact, they stay together, so what's the total mass after
Oh,
impact?
M plus M
M plus capital M,
times the
and the
velocity.
velocity is,
You don't know yet.
X dot.
we don't know.
Yeah.
Well, we call it V,
V2.
V common or something like that. But this is what I need to find out, is what is V common after impact. V common after impact obviously would be M divided by M plus capital M times Vm. Now, another interesting thing that you have to worry about when you do these types of problems is that qualitatively, right? This thing is going to move down, so you know what's going to happen, right? It's going to be just another bigger mass on top of a spring. And you're going to be vibrating. Are you going to be vibrating about this position?
Well,
Yeah.
it might.
Oh, no,
No,
no, no,
because there's
there'll
a
be a
new
new equilibrium
equilibrium.
position.
And
you're
no
right.
equilibrium. Remember, a vibrating system always vibrates about a new equilibrium state, okay? Now, because you have a new mass, remember, a new mass, that means it's a new weight, right? So the new equilibrium will be kind of somewhere here, right? And what is this distance in here? That new equilibrium position is due to what? Just due to the additional mass. Remember, mass mg is equal to k times delta, right? So this delta here will be equal to simply mg divided by k. That's the new equilibrium position. Now, based on this new equilibrium position, this condition here when the mass was there, right, will have now, remember, it's a second order stuff. We know what the mass is. What are we missing from the equation? The initial conditions, okay? So what are the initial conditions of the combined mass? First of all, the initial condition, if my x is going this way from this equilibrium, is that the initial position was where?
Negative delta.
Negative delta, or negative mg divided by k, okay? And what is the initial velocity?
Yeah.
It's whatever I calculated here. Now you got the whole thing, you can figure out everything else the same way as we did before. Okay, so let's look at the slide there.
That's what you just said.
That's exactly the same thing as I said, so it's
Yep.
nothing new, but I just want to make sure that we are. Okay, so this is the old equilibrium position, right? This is the new equilibrium position. And you see, this one is due to the additional mass that gives you that additional, movement, right? But for purposes of analyzing the vibrating system, you are analyzing it with respect to this new equilibrium position. So at time t equal to 0, my mass was there because that's where impact occurred, right? That means the location was x naught equals minus mg over k, and the v common will be the v, or the initial velocity, will be the velocity that is used to compute this equation. Okay, so I'll let you look at that one and this one. Now, how come that this is not done? It's not so. Okay. So you see, x naught, the initial velocity would be simply given by just like the equation that I have. I'm using just different terminology, but it's the same stuff. But if you look at the bottom of the slide, that shows the initial condition, initial position and initial velocity. And then from there, it's no big deal because the mass and spring stuff is going to be a problem. Okay, in fact, if you were to use the equation that you see here, assuming that x of t is equal to a cosine omega t minus v, then you would be applying the same initial condition, to figure out what.
Can I just have a little help with math? Why, to get a equal to the square root
Of this one.
yeah,
Okay.
what step went between there and
Okay.
there?
So I'm glad you asked that because, can I erase this?
Sure.
I mean,
Oh my god. It's on the side.
wait, oh.
Can you redo that?
What is back there? So we said that x of t is equal to
A cos
a cos
W,
Omega
omega
n
n t
t
minus v.
minus v, okay? But what we determined before is that x naught is equal to minus, let me go to the previous slide. Minus mg over k, right? And then x dot 0 is equal to,
Quantity m plus beta.
well, whatever, it's called x 0, right? And this is x 0, this is x dot 0. So, if xt is this, what is x dot of t? Okay, it should be quick.
Minus a omega n sine.
Minus
Minus.
a omega n
Sine omega
Sine.
n. v.
omega n t
T
minus v. Okay, so we said that at t equal to 0, right? X is equal to, that's our notation, right? X naught means the position at x equals, which happens to be this, but we don't care about that. But what is x naught in here? I have to go to x, I replace t by 0.
Zero.
So what do I get?
A
A cosine.
negative v.
So how does cosine negative phi compare to cosine phi?
Same thing.
Same.
It's the same thing. Be crazy to have cosine minus phi, right? It's an even function, right? So we call it a cosine minus phi, just to show the steps, times a cosine phi because it's an even function. And then we apply that same condition for velocity, which says that x dot is equal to x dot of 0, which is
Negative A
negative a
omega n
omega n
sine
sine
negative
negative
phi.
phi, which
same.
is, okay, sine negative phi,
Because negative
but the negative cancels out because it's an odd function, so this becomes a omega n times sine phi. Now we come back to that same problem as before.
An even function is the one with cosine and odd is with sine? Is that always the case?
No, an even function is when you have f of t equals f of minus t, or f of x equals f of minus x. So we know that cosine
Uh-huh.
fits that.
Oh, okay.
Cosine minus 30 degrees is the same thing as cosine
Okay.
plus 30 degrees. But, so this is even, right? An odd function is when you have f of minus t is equal to minus f of t, okay? Like sine of minus 30 degrees is minus the sine of 30
Right.
degrees. And a sine is a good example of an odd function. So here, we got what? We got x naught equals a cosine phi, right?
Mhm.
And then we got here x dot 0 equals a omega n sine phi. How am I gonna solve for a and phi?
Divide.
Divide, always. Divide so you can get the tangent showing up, right? Now you go like,
Would it be the omega dot?
Well,
Or
it's
omega
okay.
n
I can divide this by
Tangent.
this and make, you know, I get x dot 0 over x naught, right? The a cancels out, right?
Mhm.
It's going to be omega n times tangent of phi. Then what do? I divide by omega n, because I want to just keep tangent on one side, right? So what is, then x dot 0 over omega n, x0 equals tangent of phi, right?
Yeah.
Meaning that phi is equal to arctangent of x dot 0 over omega n x0. But how do we find a?
Initial p.
Then you come back in here. There are many different ways you can do them. You can still do a is equal to x naught divided by cosine. Cosine of the arctangent is just a nightmare. Remember what I said last week or maybe 2 weeks ago? When you have something a sine and you have something at a cosine, there is one identity that is very useful.
So the square, the sine squared equals one.
The sine square of an angle plus the sine square of an angle is always equal to 1. Okay? So what is the cosine here equal to?
X naught over a,
X naught over a. What's the sine of phi equal to?
x dot naught over a.
X
omega.
dot naught over a omega n, right?
Mhm.
Now if I can say that sine squared phi plus cosine squared phi is equal to 1, that means that sine squared is x dot 0 squared over a squared omega n squared plus cosine squared, which is x0 squared over a squared is equal to 1. Now I'll multiply by a squared on both sides. Then I end up with x0 squared divided by omega n squared plus x0 squared is equal to a squared, meaning that a is equal to
That's how they got it, okay.
It's a lot
Take
of steps
steps.
to skip.
yeah,
It really is.
really?
Yeah.
Yeah,
Okay.
That's a lot of steps to skip.
and I liked having you walk me through it, but I don't know if I can do it again.
The thing when you have whenever you have this cosine and sine, remember, it's always good to divide the equation, make tangent phi show up. I don't care how, by dividing or something
Somehow
like
make
that.
tangent phi.
And then to find the a, you just make sure that sine squared plus cosine squared is equal to 1. That's kind of usually
What's
the
that
rule.
function identity called?
It has a special name, because all of them are trig identities.
Yeah.
It's,
That's the first trig identity, I don't know.
Yeah, I
Okay.
don't know,
Alright, I
I
thought
don't
it
know
had
if it
something.
has any particular, name, but.
We can give it a name, how about
Yeah.
Fred?
Fred?
So this is how
Fred
they derived
sucks.
that,
What's that?
so when I go through all this stuff, is that how they derived that three?
Yeah, so they derived this guy here, so we just derived this, right?
Yeah.
Right.
We just derived this one.
Yeah.
Now, where did this one come from?
That's
You
a
think?
great
The front of the
question.
book.
What is
No,
which one?
no, it's easy, it's easy.
Oh, it's.
What does our, remember, our
Oh.
system has only a spring and a
Mass.
mass.
Square.
But what is the mass that's on top of the spring?
M plus n.
Is m plus m. And this one is k, right?
Mhm.
K, which is equal to 3ei divided by L cubed, right? When you have a mass spring, there should not be any ambiguity. When you have a mass spring, omega n is always equal to the square root of
K over.
the mass, of k, right? K divided by the mass, but the mass happens to be, in this case, m plus m. Okay,
And
so
K-
there's nothing new.
And
in
K we
this.
get from the beginning, the front of the book.
Yes, And the K you get in the beginning of the book, now if you can replace this by that, that's what you get in there, right?
Gotcha.
3EI divided by L cubed, right? And plus M. So the equation may look like complicated, but it's really just based on square root K over N.
So when was the last day to drop? No, I'm just
Last Friday.
Last Friday.
Last week.
We're gonna
Alright.
get through this.
kidding.
May not be pretty.
They're just called the Pythagorean identities.
We can
Thank
do
you,
it.
yeah, that's something.
Oh,
All right, now we've been talking about just a mass attached at the end of the spring, but in reality, you can also have vibration that is associated with a torsional system, okay? In other words, you could have a bar, which is called a thin, maybe prismatic bar, at the end of it, and we will be doing one lab like that, by the way, in which we'll have a disc at the bottom of it, a heavy one, and then what you do is you just push the disc from equilibrium position, and then let it vibrate. It's going to vibrate in the horizontal plane, okay? So if a rigid body oscillates about a specific reference axis, the resulting motion is the torsional system. So because now the vertical axis, you know, you're rotating with respect to that, we call that torsional one. The displacement is not going to be an actual displacement, but it's going to be angular displacement, which is so we need an angular coordinate, which is like theta, for example. In this vibrating system, when you have a mass at the end of the spring, what tends to bring the mass back towards equilibrium?
Damn.
Remember, simple harmonic motion is a motion where the acceleration is always equal to a negative value times the displacement, right? X dot dot equals minus omega n times x, right? So if you are on the right-hand side, the acceleration is to the left.
Proportional dis-
If you're on the left-hand side, the acceleration is to the right. So for a mass at the end of the spring, it's really the spring force that tends to bring you back and forth, right? But for a restoring, for a disc, it's going to be, what generates rotation? Is that a force or a couple or a torque? Couple or torque, it's the same thing, you know? It's a couple or a moment, right? That means that what brings you back is, again, that restoring moment, right? Anytime you're beyond there, it tends to bring you back. You go beyond the equilibrium position, then it changes sign. It tends to bring you back and forth, okay? A schematic of this will be here, and I'm going to erase this guy. Think of a shaft, as you can see here, but then at the end of it you have a spring. I don't know if you guys remember this or not, but if you have a bar like this that you pull with a load P like this, right? The bar has a certain length L, right? And a cross-sectional area A. What's going to happen to the bar in the elastic range? It will elongate, right, or extend. It's going to extend maybe by an amount which I call maybe delta. What is delta a function of?
PL over A or something.
Delta equals
PL over A.
PL, well, you guys remember, good. PL over
That I can
AE.
remember.
PL over AE, exactly. Okay? Now, in rotation, remember there's always great analogy between translation and rotation, right? So, if you remember in strength of materials, in translation you have sigma equals E times epsilon. You remember this equation? In the stress strain diagram, in the linear part. What is the equivalent one in shear? Shear stress is equal to
G?
G, yeah, thank you. G times what? What is the shear strain? What is the sum?
I
of the-
don't know. Modulus.
It's gamma.
Gamma.
Right? It's gamma. This is the elastic modulus, and this is the shear modulus, okay? Now, the reason I'm saying this is just to kind of bypass a few things. What is the deformation, by analogy, what is the deformation that is associated with rotation? For elongation, it's going to be this, right? If it's a bar that is in torsion, for example, instead of
Shear.
delta.
Pretty sheer.
No, this is delta, this is a displacement.
Oh, sorry.
So you use an angular
Theta.
Oh, of course.
theta. It's an angle that you use for rotation instead of x, if you will. So instead of load P, what causes?
Torque.
It's torque, or we call it moment in our case, okay? And here we have obviously, the length is the length of the bar, right? Except that instead of you're applying this, you're applying a moment in here, right? And a moment there, right? So it's going to be L. Instead of an area, what should we put in there? Remember in dynamics, let's take a little thing. Anytime we had a mass for linear motion, for angular motion, we were replacing it by,
It was theta, right?
no,
Oh, it was I.
what was I, which is the mass moment of inertia, okay? Here, it's not mass, it's area, so in rotation it will be same thing, kind of area moment of inertia, okay, which is I.
Is that the same thing as mass moment? No.
No, it's different.
So-
So the area moment of inertia has a dimension of length to the power of 4, you know? It's the
Okay.
stuff that you do in bending and in
Oh,
plane stuff,
oh.
right? And then instead of E, it will be
G.
G. There you go. So based on this, if you look at that equation at the top, isn't it true that I can say based on this equation that M is equal to G I divided by L times
Theta.
ML is equal to theta, right? What the heck is theta?
Yeah, but theta, you need theta. Yes.
Cause you're, yeah.
Okay. So that's where that equation comes from. That's all I meant to say, okay? See, vibration kind of contains a lot of things from the past. It comes back and haunts you.
Yeah, that's the
So
right
is-
wording.
Is area moment of inertia the same as polar moment of inertia?
Okay,
Oh,
what is the difference between polar moment of inertia and area moment of inertia?
One is Cartesian and the other is.
Well, if you have a rectangular surface like this, right? Remember the area moment of inertia is typically described with respect to the centroid of the surface. So you could have an area of moment of inertia Ix, x, right? Or you could have it as I, y, y, and I give you kind of a little thing from strength of material. When you have BH here, right? If you guys remember, I is equal with respect to this horizontal axis is BH cubed over 12. But with respect to this axis, it will going to be HB cubed over 12. Okay? But that's more strength of materials and machine design and all kind of stuff. So we're not gonna get- But all we were saying is that when you have IXX, IYY, if you want to find what is I with respect to O, then that's going to be equal to IXX plus IYY.
uh-huh. And that's polar
This is the polar moment of inertia.
because there's.
Because you are doing it, the polar moment of inertia, you are doing it with respect to a point.
Okay,
Whereas the other ones,
Instead
you
of
are
an
doing them
axis.
with respect to an axis.
got it.
That's the key difference.
Thank you
Alright,
for
alright, getting
making
back
this
to
simple.
way back when.
I mean,
So MT here is the torque that produces the twist theta, G is the shear modulus, L is the length of the shaft, I0 is the polar moment of inertia, which for a circular surface is pi over 32 times d4.
that's in our book, right? In the-
Should be,
Okay.
yeah.
Do I have to memorize that?
Pi over 34 I don't know where I have to find it though.
Page 146.
Page 146.
It's not in the front of the book.
Bob Saget.
Well, in any case, you know, I with respect to O is pi over pi d4 divided by 32. So this is a polar area moment of inertia, right? Now, whenever you go there and go like, okay, now what the heck is, based on this one, so we can continue, what is this stiffness of this spring? What is the stiffness of this bar, by the way? We talked about this last week, 2 weeks ago.
2 weeks
I
ago?
remember
Do you
yesterday.
agree that this is like a spring?
Yes.
Is my
Yeah.
question.
Yeah.
And how do you typically figure out what is the equivalent stiffness?
I think it's KX.
You write it in the form of load equals something times displacement, okay? What is the load here?
P.
P equals to something, what is the displacement?
Delta.
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 So if I rewrite this in this
Over.
form, what do I get?
Ah.
P is equal to
AE
AE
over
over
L
L times delta. That means that this guy is the K equivalent.
There you go.
Now, for our torsional stuff, right? What would our equation be? Here we were trying to write it as load equals this times that. But for rotational, what would it be?
You've already got it right there. M equals GI.
It should be moment instead of load, it should be moment is equal to something times what?
M theta.
Theta, exactly. Okay? Now if I rewrite this in this
Right
form,
there, which you already did.
which I already did. So this is K equivalent.
Okay.
Okay? So it's all equivalent. Equivalent, you write it in the equivalent form of moment equals something times that, and then you get it, okay? So that's why here we have KT is equal to MT over theta, which is GIO over L, you know, and the rest.
Oh, they just broke it out a little bit more. They broke
Yes.
out I.
You know, and then they just replaced I by this guy, okay?
Yeah.
Now, what the heck is J here?
Oh, that.
That's another one of those inertia things. What was it?
Do you think J is an area moment of inertia or something?
Probably not. Oh,
It's a mass moment of inertia.
inertia.
Because from dynamics, when you have something that is rotating, right, you are applying the load
Point. Yeah.
to the thing and then it gives you the value, but we're not gonna worry about it at this
Not worrying about
point
it yet?
because,
Newton's second law.
yeah. For a disk, you just read it off tables, what is the value of J for a disk. Now, what is the equation? Again, the reason I'm going through this is I want your head to be kind of in the analogy form, right? Because the one that we spent time on, the equation that we spent time on is the equation that kind of looks like this. And that's the one that, by the way, you should always remember. Mx dot dot plus Kx equal to 0, because we haven't talked about damping just yet. Right? So, if I want to write an equation for this, but associated with something that is rotating, what would replace M? We talk about this in dynamics all the time. What replaces M in a rotation?
I.
Well, in this,
J.
we call it, in this book, he calls it J, which is
But
we'd
we'd
moment of
always
inertia.
call it. Oh.
You can call it I, but the
Call it
reason
whatever.
is this book uses I for area moment of inertia and then J for
The
mass
mass
moment of
moment.
inertia.
Right.
In dynamics, we typically don't have those occurring at the same time,
Okay.
okay? So, and then instead of X, it would be what?
KT.
Theta.
Theta. Theta dot
So
dot.
theta dot dot plus, what is K? Well, it's still going to be
Still
K,
K.
but except that it's K for maybe a rotation, just to kind of, and then theta
Now you're doing different-
equal to 0. Is this differential equation any different than from that?
No.
In terms of solution, getting a solution for it?
The
It's
characteristic
exactly the same.
equation is identical.
And this one would still need 2 initial conditions, which are what? Theta at 0 and
Theta dot.
Theta dot at 0.
So
Okay.
the second one is for rotation,
This one is for rotation, yes.
and the first one is for just.
Translation.
This is just
Translation.
translation, if
Okay.
you will.
What's the sub decay?
Just
Rotation.
for
Oh, that's an R, okay.
It's just an R, you know, just, I just added R, I don't know.
I couldn't
if
tell if it
it's
was a
okay.
V or
They
an
have
R.
K in
It's
there,
just
or
to, just
T,
to
they
make
have
sure that
T.
you don't think it's the same K, that's
Got
all.
it.
It could still be
Yeah.
K.
Just a different type of K.
So the equation for angular motion of the disk about its axis can be derived by using Newton's second law, obviously, but we're not gonna even do that. We're just doing it by analogy. And now, if the equation is given like this, then what is the frequency of that disk is gonna be turning with? What is the natural frequency? Shouldn't be any hesitation.
KT over.
Okay.
What is the frequency here, omega n?
Oh, root, that's right, root K over M. So it'd be
So what
root,
it would be
root
here?
K over J naught.
Okay, there you go.
Okay, sorry.
K over J naught.
It'll get there.
Analogy.
By the time it
Analogy
first-
saves you a lot, no? So when you write that equation, that's it. So omega n is kT over J naught squared is the natural frequency of vibration. And the general solution now can be written just as we did it for the mass, as either in this form, a cosine omega t plus a2 sine omega t. What are the unknowns in here? Obviously, it's a1 and a2, which we can get from applying the initial conditions. Okay. Do you wanna go through how we find this one?
Would we like that for
Sure.
the test?
We would like that for the test.
Yes, I think we would.
Well, if you look at this form of the solution, remember the solution is looking like, let me get this darn book here. So I can look at my screen because I can't see your screen. So theta of t is going to take this general solution, which is a cosine omega n t plus b sine omega n t, okay? At t equal to 0, theta is equal to theta naught, right? Now I replace here t by 0, so help me.
Cosine zero is 1.
Cosine 0 is 1, so I'm just gonna have
Yeah.
a here. How about here?
Nothing.
Nothing. Okay, that was easy. A is equal to cosine this.
Equals theta naught.
So what is the theta naught? What would it be? Okay, I have to first find an expression for it in general.
Minus A omega N cosine.
Minus a omega n sine omega n t
Plus
B
omega N
omega n
cosine.
cosine omega n t. Now I apply my initial condition. Theta dot equals theta dot 0 equals, now I replace t by 0 here. This term does not contribute,
Right.
but this one would be simply
B
b
omega N.
Omega n
omega
squared.
n, just omega
Omega
n,
n, sorry.
right? Which means that b is equal to
Theta dot naught over.
theta dot
omega N.
naught over omega n. Okay, which is the same thing as we have in the slide. It's always the same methodology. I mean, there's nothing new, you know? Okay. An example of this is, for example, finding what is the natural frequency of a compound pendulum, okay? A compound pendulum is, you have any rigid body that is, it's not a pole, it's not like a cord with a mass at the end of it, but any rigid body that you are rotating with respect to a point that is other than its center of gravity, right? So, any rigid body pivoted at a point other than its center of mass will oscillate about the pivot point under its own gravitational force. Such a system is known as a compound pendulum, okay? So if you look at this schematic, right? What is the fixed point of rotation? It's obviously, it's this point right there, point up, right? So remember the equations of motion from dynamics is that sum of the moments is equal to,
Oh,
it's not zero,
Sorry.
Is that me?
MA.
it's not MA,
Oh, sorry,
it's rotation.
So.
Oh, that,
something
I-
I omega,
In this case, we call it J,
J.
J omega.
J, it's, no, J alpha,
Oh, that's right. Net velocity.
which is theta
acceleration.
dot dot,
Yeah,
the
yeah.
second derivative of the angle, okay? So the moment here is fairly straightforward because the moment, there is only one force that causes a moment with respect to point O, which is what? mg. So what is the moment of mg with respect to point O? It's
Point
mg
oh,
times,
MG, B,
times, which, times this distance or times this
B-
horizontal distance?
B to G, I guess, not the horizontal distance, it would be it would be this, I guess,
It'd be the,
W sine theta, plus B. Sorry, I'm sorry, that's
Times.
I think that moment is a
W
force
cos
times
theta plus
distance,
B.
right? We agree.
Yeah.
The force is pretty clear, it's mg, right? But what is the moment arm of this force?
It's OG, it's D.
It would actually be about point G, right?
D
It's not
sine.
gonna be OG, no.
D
So
sine.
it would be W cosine,
Well, if I have
Theta
something like
times
this.
B.
Okay, let's say I'm rotating about this point, right?
mhm,
And let's say my center of gravity is right here, right? And my weight is right there, mg. And I wanna find out the moment of this force with respect to point O, okay? This moment is always has to equal the force times the shortest distance between the two. So you have to extend the force, the perpendicular distance between the two. Because if my force is here, its moment arm is zero,
Zero.
okay? So I need to find if this distance is known, is that one given?
It just says D.
It just says D, that
D.
means that, and this angle is, what angle is defined? Is that
Theta.
theta, right? So that means that this is theta, that means that this distance, which is the moment arm, is
D sine theta.
d sine theta. That means that the moment is actually mg times
D sine theta.
sine theta, but theta is defined as positive in this direction, so that means that this guy is doing the, kind of going negative, if you will.
Should that be D sine theta?
D sine theta is equal to J naught times
Alpha.
alpha, but
Or
alpha is
theta dot dot.
theta dot dot, right? Now we come back, put everything on one side, then you get J naught theta dot plus mg times d times sine theta is equal to 0. Now, is this equation, what kind of equation is this?
That
equation of
is
motion, right?
Standard.
It's an equation of motion, that's true.
Harmonic.
No, it's a differential equation, right? Because it involves
Second
a
order.
function
order
of its
differential.
derivative, it's second
Periodic.
order. Is it linear?
No.
No.
No, because it's got that stupid sign in there, right? You probably heard many problems before in physics and many other things, and it says, when the angle is really small,
Yeah.
why do they tell you that?
So you
So
can
that
make
you
it
can
an
make it
ordinary
almost
equation.
Exactly, see, because when the angle is small, then sine theta is the same thing as, can be approximated by theta, and then suddenly my equation now becomes J naught theta dot dot plus m g d theta equal to 0, and this is a beautiful equation because I know how to deal with it.
Now it's an ordinary.
It has that same form of, you know, m or something, xx dot dot plus kx equal to 0. We know what's the natural frequency of this. What is the natural frequency of this, by the way?
Square root of,
Square root of
mg
K
over
MG.
J naught.
MG D over J
mg
naught.
d over, yeah, you guys are rocking, that's good. See, by looking at the equation without doing much, you can get a lot of information.
So why does the seems like you're going through a lot more depth than the example in the book. Like it just kind of.
Because he's cool and the book's not.
And the book is terrible.
Oh, the book doesn't,
The
It
book
doesn't
is
go
Sufi
through
Dodo.
any of
The
it.
book
It
is
just-
Dr.
it just
Bean.
gives you-
seems
it
to
just
go-
gives you that, that's why
It doesn't-
I'm doing this, you know, it's because they, yeah, they don't give you all the steps.
The book is
They
like
leave-
Dr.
they
Bean.
leave out a
Okay, it
lot
seems
of
to know
stuff.
everything.
And
That's
this
why
book
I
is
asked
thick.
the question,
Yes.
The
what-
book is pretty darn thick, right?
Alright, I
You
take
would,
back what I
you
said
would
earlier
think
about this
that
book.
you go like, oh, you
Did
know.
you like it?
Yeah.
I liked it
So-
better than the fluids.
So in any case, you know, that's kind of how you derive the equation, and then from there you get, you know, you make the approximation, and you get J naught theta dot dot plus WD. Well, he calls it WD, I called it MGD, but that's the same thing because MG is W, right? Equal to that, and this is your good old frequency, okay? And we stop it right there. WD divided by J naught. Now you can predict how the darn thing is going to vibrate.
That's only when the angle is small.
When the angle is small,
Will
yeah.
we be working when the angle is
No,
not
no,
small?
we're not gonna venture there,
Oh,
you know. That's when you do numerical analysis, because then you can program it to do that kind of stuff. But to find an analytical solution, you have to assume that it is, that the angle is small. Okay, moving on now to the response of first order system, because pretty soon we're gonna start with damping, right? In fact, we're starting with damping right here with just first order damping. Okay, what does first order mean? That means you end up with a first order differential equation. First order meaning that the highest derivative is the first derivative, okay? Now, if you consider, for example, a turbine rotor that you see here, that has a certain mass moment of inertia, J, and then you have the viscous lubricant in the bearing offers viscous damping torque. Remember, damping, viscous is one of the key ones during the rotation of the turbine motor. So the thing is rotating, but you got some damping. Remember what's critical, what do you know about, what is the important information we know about viscous damping? What is the thing?
Thing?
What's that?
The thing? Like it's related to velocity?
Exactly, that's related to velocity. What is it? What is in a viscous damping, right? How is the damping force, almost giving you the answer.
It's,
How is
The
the damping
damper?
force related to velocity?
The density.
No. The damping, for a spring, the force is proportional to the displacement.
displacement.
The constant of proportionality is the spring constant. For a damper,
Oh, it's the inverse.
the force is
Inversely
proportional to the velocity.
Velocity.
And the constant of proportionality is the damping, okay? So for a spring, F equals Kx, right? This is the spring constant. For a damper, F of
C.
damper is
C
equal
of
to
E.
C times,
Velocity, alright.
that's what you need to remember. That's why we always do use viscous dampers, and we don't even venture into Coulomb damping and all that kind of stuff, because that's just a big headache. But this one, for a damper, that's great, okay? Now you have this motor that is turning, right? It's on a shaft that is on bearings, that is a lubricated bearing. And obviously, because we don't need to go into details what the heck is happening there, it's Newtonian fluid and shear stresses get developed, boom, boom, boom. But the bottom line is there will be a resisting what?
Force or moment.
A resisting moment, right? So, so in this particular case, the equation of motion is going to be equal to what? The only force that is acting on this rotating stuff is what?
The damping.
It's just the damping. And what did we say about the damping? It's
C-
proportional to
The velocity.
The velocity. But what kind of velocity in this case? Is it linear velocity or rotational velocity?
Rotation.
It's rotational velocity, which is technically theta dot. But you know what theta dot is from dynamics, right? We have another name for it. Remember theta, and then d theta over dt is, call it omega, right?
A different omega.
It's angular velocity, yeah.
Yep.
Not the,
Not the omega n.
No, not frequency, yeah. But it's still an angular velocity
Yeah.
in here. So here we call it minus c,
Omega.
well, let me call it c theta dot for now.
Yeah.
That's the only force. Sum of the forces is equal to what? It's rotation, so it's instead of ma, it's going to be j
Or
naught
alpha, J naught alpha.
times
Alpha.
alpha. Okay? But alpha we know is theta dot dot. But now I know that I can come back here and say, hey, this one is omega, right? And theta dot dot is simply omega dot. I have every right to do
And
this.
we have C being negative because it's a damper.
Because
and
it is
it's
resisting,
taking
yes.
out- yeah.
Right. So now if I put everything on one side, I'm gonna get zero, j naught omega dot plus c omega is equal to 0. Okay? First order differential equation. What is the method that we typically use to solve first order differential equation? No.
What's that? No?
Well,
Did
not
you say
whatever you
calculate
choose,
it?
you know.
Uh,
We use separation of
Understanding.
variables, right? But how many initial conditions would you need to have here, you think?
One.
Because it's first order. Okay, so usually it's given by the initial conditions, which is at t equal to 0, right? Omega equals omega 0. Maybe my motor was traveling at a certain angular velocity. So how do we solve this? I'm just gonna show you that. You don't need to worry about it. So g naught times omega naught, I will write it as d omega over dt is equal to minus c times omega. So when you do separation of variables, you get the time on one side and you get the other stuff on the other side, right? So I could say, for example, that d omega over omega, right, is equal to minus c over j naught times dt. Do you agree that this is the same thing as this?
Yes.
Then what do I need to do here? I need to integrate between 0 and t. What are my limits of integration here? What should I write here? Well, at t equal to 0, omega is omega naught. And at t, it's just omega. So what is the integral of d omega over omega?
What is it, natural log?
Natural log of omega. So the natural log of omega evaluated between omega naught and omega equals minus c over j naught times t. But this one is log of omega minus omega 0, which is log of omega over omega 0. So how do I go from omega over omega 0? If you take the exponential
Yeah.
of a log,
Then you take the exponential of both sides.
then I take the exponential, so the exponential of a log cancels out, right? And then this one becomes simply exponential of minus c j naught times t.
Do
What
we-
does this
But we
equation?
don't have to know
Yeah, do we have to know how to do that?
Pardon?
Do we have to know how to drive that?
No, I'm not gonna ask you to write this. But this should be kind of common knowledge
this. It should be common.
for first order. I mean.
Oh, right, yeah.
I
So
don't
we
know
don't
what
have to
happened.
drive it, but we have to
But
know how to
it's
get
to
it.
know how it came about, okay? So here it tells you that omega is equal to omega naught times exponential minus c over j naught times t, okay? It tells me exactly how that angular velocity is going to be changing as a function of time.
Angular velocity of the rotor.
Of the rotor, yes,
Okay.
yeah, obviously, of the rotor, because that's the mass, that's.
Obviously, so
Yeah.
I apologize.
Oh, sorry.
What's wrong with you?
Remember, when we're talking about linear systems, right? We have masses. The springs and the dampers are just peripherals, I guess we call them, that control how that mass is moving. But anytime we solve for x, we are really solving x for the mass that is moving. And its rotation is about whatever is rotating. Like if it were for the disk, it's not the shaft of the disk, but it's really that disk itself, okay? In this case, it's not the motor, it's the motor, but not the shaft. The shaft is just a means of.
I trust them that the time constant which corresponds when the response is reduced 0.368 times its initial value is.
Yeah.
But how did they get 0.368?
Okay.
And you don't have to do it, just that.
It's a quick one,
Okay.
believe me. So omega is equal to this, right?
Yeah.
I can write this equation as exponential of minus t over J naught over C. Have you taken electrical stuff classes where you did the capacitors charging and discharging? Every time we do those, we talk about time constants, okay? Why is it time constants? Is if when you write it like this, when you have exponential of minus 1, when do you get exponential of minus 1? Only when t is equal to, when t is equal, when the denominator is equal to the numerator, right?
Right.
That means when t is equal to j naught over c. So we call this time, the time constant, which is j naught, I believe, over c, because the exponential of minus 1, if you look in your calculator, that should equal to 0.368.
368. Okay. So it's just
Okay?
that natural.
And then what does it mean? That means when t is equal to this, omega over omega naught is equal to 0.368, right?
Okay.
Meaning that omega is equal to 0.368 omega naught. So if you look at that last thing that we're talking about, the time constant which corresponds to the response to reduced when the response is reduced, the response is reduced to 0.368 times the initial stuff. Okay? So in other words, if you look at the plot here, when t is equal to 0, omega is equal to what? Omega 0. So this is how that angular velocity of the motor, it's going to be decreasing, because when t approaches infinity, what's going to happen to omega? It will approach 0, right? So it will asymptotically approach 0 in this fashion. Okay. Moving on to a newer section.
Yes.
The newer section called Rayleigh's method. Rayleigh's energy method. Rayleigh's energy method is Rayleigh's energy method is, can I erase this? Okay.
Yeah, we're good.
Sorry.
He's a smart
Well,
ass.
last week, by the way, or 2 weeks ago, we developed the equation of motion of a mass attached to the end of the spring using how many methods?
3.
It was 2.
Well, you did it by hand algebraically.
Oh, no, not that.
Oh.
I mean, finding like the equation for when you have this and then the mass, right? We did it first using the free body diagram, saying that, okay, if this is x, when I pull this guy from equilibrium, I think we did it for a mass that is horizontal, right? Right? It's in equilibrium, and then when we pulled it to this, we did the free body diagram, right? Said, hey, when you pull it this way, you're going to have what?
Yeah.
Minus kx, right? That's the only force acting on this, so we said minus kx is equal to mass times acceleration, which is mx dot dot, and therefore we get mx dot dot plus kx equal to 0.
Right.
But
Oh, now we're adding it.
is this system is not damped, right? That means that energy is conserved. We also did it using the energy conservation, and we said that the energy conservation here is E is equal to,
MC squared.
no,
sorry.
What is the spring energy? It's
KX
1/2 of kx squared, and the kinetic energy of the mass is
1/2
mv
squared.
1/2 of m x
X
dot
dot
squared.
squared.
And because this E is constant, right, the second method that we did said that dE over dt should equal to what? If E is constant, dE over dt is 0. You know, when derivative of constant is always 0. So if I take the derivative of this guy and remember my chain rule, right, then I get what? I take first the derivative with respect to x, and then multiply dx over dt, right? So you get derivative with respect to x will be
KX.
kx times dx over dt, which is x dot, and here plus taking the derivative now with respect to x dot,
2m, or m.
which is m x
times
dot, and then take the derivative of x dot, which is x dot dot, equal to 0, and then you simplify by x dot, and then you get mx dot dot plus kx equal to 0. See, it's another way of finding exactly the same equation. Now Rayleigh comes in and says, hey,
Let's give you a third method.
in the vibrating system, and we talked about this before, the energy is being balanced, tossed, I should say, maybe is the word, between the mass and the spring, you know? Because when the mass is at its extreme position, what is its kinetic energy? 0. And the spring is the most stretched, so the potential energy of the spring is highest. When the spring, when the mass goes through the equilibrium position, the spring energy is 0, but the kinetic energy is the highest. So Rayleigh comes in and says, hey, that means that really T max is equal to U max. The more, because you're exchanging between the two, right? So the maximum kinetic energy is the same thing as the potential, as the maximum kinetic energy is equal to the maximum potential energy. So, with this said, if you look, for example, at a situation where you have x is equal to, let's say, x of t, because this is a harmonic motion. Let's say, for example, it's a times cosine omega t plus v, let's say. Let's pretend. Based on this, what is x dot equal to?
Can I have a quick stupid question?
Yes,
T max and U max,
yes.
what are they?
This is maximum kinetic energy,
Okay, kinetic and potential.
maximum
Okay.
potential energy. So if x of t is like this, what is x dot of t?
Oh, it's a sine, a omega n sine, or negative a omega n sine omega n t plus v. Keep
Okay.
doing it, we'll never forget.
Now, if you have this, what is then, what is the, what is U max in here, you think equal to, based on this? Well, U max is maximum kinetic energy, potential energy of the spring, right? It's 1/2 of k times the maximum displacement, right? But what is the maximum displacement if this is what describes it?
1. Oh, sorry. Would be a.
It would be A. Remember, that's the amplitude of vibration, right? So it's going to be 1/2 of k A squared. Because A, remember the maximum value of a cosine is 1. That means that if my mass, the maximum displacement it's going to go from equilibrium will be A, right? How about the kinetic energy? Well, it's 1/2 of m times, what is the maximum kinetic energy based on just, what is the maximum velocity based on this equation equal to?
Oh,
Talk about this last
we
time.
did,
Yeah.
it's in my notes.
What is maximum kinetic energy? It should be, remember, the maximum value of a sine is 1,
Yeah.
right? So the maximum kinetic, the maximum
Minus a
speed
omega n.
is a omega n,
squared.
right? So it's gonna be 1/2 of m times
A omega n
a squared omega n squared. Do you agree? Because it's x dot squared, right? Now, what does Rayleigh tell me? It tells me that this should equal to that, right? 1/2 of k, a squared is equal to 1/2 of m, a squared omega n squared. I can get rid of the half, I can get rid of the a squared, and then what do I end up with? I divide by m on both sides, k over m equals omega n squared, meaning that omega n is equal to square root of
Oh, it's the same
k over
thing.
m. What? No way. There you go.
You're telling the truth the whole time.
Now we believe
Three
it.
different ways of looking at things, okay? So this is the Rayleigh's
That one
method,
seems like
which-
it's the
and
easiest
this
one.
method, this third method is useful for different things, okay? When you have a big mass and then you have potential energy that is associated with that, you can actually solve the problem using this. In fact, there's one problem that is given to you here,
Omega n is the
natural frequency of
natural
vibration.
frequency.
Yes. So that's how it's going to, and m is whatever mass is attached to the end of the spring. Okay? So in other words, without solving the equation, you know, we are determining what the natural frequency is, without deriving the equation itself, okay? And which is really the goal of the whole thing anyways. An example that is given to you here is, you got a manometer of a diesel, for a diesel engine. We know what manometers are from what we've been doing in fluids. So the exhaust from a single cylinder 4-stroke diesel engine is to be connected to a silencer, and the pressure therein is to be measured with a simple U-tube manometer, okay? And I'm just gonna do the first part of this problem, I'm not gonna do the deep part of it, okay? Because it's really pointless. Calculate the minimum length of the manometer tube so that the natural frequency of oscillation of the mercury column will be 3.5 times slower than the frequency. He complicates the problem for no reason, really. 3 times this, okay? So the part that I'm interested in is this one, okay? And you can probably imagine if you have a U-tube, right? That's filled with a certain liquid, right? And then you push that liquid on one side, and then you release, what's going to happen? Right? So there is some frequency, right? What is the mass that is moving in here?
Half
Is
of the
it the
water.
liquid?
It's the mass of the liquid that's inside, right? Now, how am I gonna get the darn equation for this, a free body diagram or something like this for this one? This is not like a mass that is
Yeah,
attached to
what
the
would
end
your
of the
spring
spring.
be?
Would be the center of mass.
Well, see, that's the kind of the property of that, of the system itself. So cannot tell just by looking at it, but it is the only way you can figure this out is to go, let's what is it called? Displace it from the equilibrium position. This is the initial equilibrium position, right? Let's say a certain volume gets pushed down and the same volume actually goes up, right? Because I don't know any better, I cannot use this method, nor can I use that method. The only method that's available for me is the Rayleigh's method, which tells me that, hey, if it's a vibrating system, that means that the potential energy better be equal to the maximum. The maximum potential better be equal to the maximum kinetic. So that's the only thing I can go with. Now you go and look at this system, you say, okay, how much mass do I have here? if this distance is x, okay? Well, I guess it depends on
Density. Or
the density,
specific-
or, like for example here, it's the, if we wanna look at the weight, for example, because gamma obviously is
Specific volume.
specific weight,
Weight.
okay? I hope it's specific,
Yeah.
right?
Of the
And
fluid.
A is the cross-sectional area of the tube, right? And x is this height, that means AX is the volume. If this is the weight per unit volume, that means really this is the weight of this guy, right? But why are we multiplying it by x over 2? Just this. Because the
Centroid.
centroid of this mass is right there, right? So if you look at that mass will tend to do what? It wants to come down by distance, which is x over 2, to come back to equilibrium. And the same thing for this one that went down, right? That was pushed down, wants to go up again by ax omega x over 2, right? So that means that the total potential energy is really the sum of this guy and that guy, right? So if you look at the analysis, the natural frequency of oscillation of the liquid column, you know, based on what we just talked about, U is the potential energy of the raised column plus the potential energy of the depressed one. Height one, the depressed one, and they have exactly the same because it's symmetrical. Both of them want to come back to the equilibrium position. When we do this, it's AX gamma divided by 2, which is the, when you sum them, you get A gamma times X2, right? But by Rayleigh's method, we have to say that it is equal to how much? The maximum kinetic energy, okay? The maximum kinetic energy is 1/2. The mass is really the mass of the mercury, right? Times the velocity squared. But what is the mass of the mercury? Look at this, it's AL times gamma. What is L? L is just the length of the entire mercury thing, because now we are getting the entire volume, right? And we are dividing by G because weight divided by G is equal to mass, right? So based on that, now you can get your equation and do the rest, which we're not gonna do here because everything else is, you know, once you have your equation, you have your natural frequency, you are actually in business. Okay, so I'm gonna do the rest. Now this is where the viscous damping starts. Now we are done with the conservation of energy. Now we're gonna introduce that third part. The third part is when you have things that are going sinusoidally, but there is damping, right? So what is the outcome? If you have a sinusoidal motion and you put damping on it, what can happen?
It's gonna go to 0 eventually.
Well, it depends how much, yeah, it will eventually go to 0, but what kind of damping are you gonna have? Is it gonna go to 0 immediately?
No.
It's gonna go this, or it's gonna take some time, right?
Attenuation.
And again, you can't tell just by looking at something, obviously, it's all equation, controlled. Now let's look at this system right here. Before we did it with just a K, right? Now we're adding this damper. Remember, what you need to remember about the damper is that the force developed by the damper is always proportional to
The velocity.
the velocity, okay? Because this one end is fixed, this velocity is the velocity of the mass, so the force that develops in this damper would be equal to how much? C times x dot. Whereas the force that develops in the spring is kx. So as I pull the mass down a distance x, right, the spring wants to pull it back with a distance kx, and if I pull this mass, and then the damper will always be opposite, obviously, the direction of motion, but it is opposite in a sense that it is equal to cx dot c times x dot. Looking at this free body diagram here, what can we say? Well, we know that sum of the forces is equal to mass times acceleration. So, what is the sum of the forces? Look at this here. It's minus, because x is pointing downwards, So it's minus Cx dot minus Kx. Those are the only two forces acting on my system, and they should equal to what? Mx dot dot, which is Ma, okay? So that's why the key equation of vibration always takes up the form Mx dot dot plus Cx dot plus Kx equal to 0. Now, when C does not exist, the equation becomes very simple, right? Omega n becomes very simple, and the solution is harmonic. We can guess that, we can find the initial conditions and all the rest. The moment you start introducing this, a lot of stuff happens. Because it depends on what is the value of that damping, okay? So, but one thing we know though is that this equation is a second order differential equation. Just same thing we did last week in, 2 weeks ago in the lab. How do you solve this? This is homogeneous, right? That means we're not forcing it yet. That's gonna come back down the road. But for now, you have a system that has damping, you pull it from, it has still x0 and x dot 0, and you want to figure out what's going to happen afterwards, okay? So, this is not a something to guess. It has to be controlled by what? By the equations of motion. We have no choice but to write the equation of motion. That means you have to solve this. How do you solve this? Obviously, you write your characteristic or auxiliary equation that we talked about last time, which is in the form of ms squared plus cs plus k equal to 0. How many roots do you have for second order? You have 2 roots, right? S12 is equal to, like here, minus c plus or minus square root of c squared minus 4 mk divided by 2m. You guys remember the quadratic stuff? So this becomes essentially minus c over 2m plus or minus square root of c squared minus 4mk, and I probably include this guy inside the radical. If I push it inside the radical, what does it become? 4
M squared.
m squared, right? So this becomes minus c over 2m plus or minus square root of c over 2m squared, right? Minus k over m, something like this. 2 roots. Now, the 2 roots are going to take an interesting turn depending on the sign of what's inside the radical here. Okay, this is the controlling factor, okay? But in general, the way, when we write this equation like this, the solution becomes in the form of x is equal to maybe a es1t plus a2 es2t. Okay? You see here?
That's based off, so that equation you just wrote, that's based off if, cause there's like 3 different types, right? If it's real
Right.
and same, real and different, and.
But this one is the, that one there,
Uh-huh.
A1 or S1T, or, that's the general form.
That's always the.
Yeah, that's general form, it looks like that, but obviously, when some factors there are negative, you can have some imaginary values, then we're gonna go through each one of them separately.
Yeah.
Yeah, but this is kind of the general, if you look here on the screen here at the top, it's gonna be C1 exponential minus C over 2m plus this times t. So this is the general form of the solution, okay? Where C1 and C2 are arbitrary constants, where do we get them from? Obviously, we get them from the 2 initial conditions.
So S1 is the top one, S2 is the bottom, you just plug it into that.
Okay,
Yeah.
That's a big ugly mess.
yeah,
Yeah, I didn't want to write it like in this form because it's just too long, okay?
alright, so I
So,
got it.
let's look at, we'll start first with
Well,
the situation. One situation is when this guy is equal to 0. you know, that means you have C over 2m squared equals K over M, right? That means that C over 2m is equal to, I guess, square root K over M, right? That means that C is equal to 2m square root K over M, which is 2 square root of Km, okay? We call this the critical damping.
Could you be funny and say 2m
Or
omega
2,
n?
2m, yeah, we could, you know, because still square root of K over M is still omega n, right? But for now,
Is
lot
that
of
how they got that 2m omega n? On,
how? Because
well, yeah, so
Yeah,
they
so-
just substituted.
Yes.
Yeah,
because
so-
I could have said
Yeah.
here
2m
2m
omega
omega n because this square root K over M is that, okay?
n.
But sometimes, the reason I wrote it like this is because in most cases you are given a spring and the mass, so you go immediately find CC instead of calculating it through omega n. I mean, that's just my thing.
And this is what you'll use for critical damping?
Yeah, that's the critical
This
damping.
is, that's the, okay.
Yeah. So what happens when you have critical damping? When you have this equal to 0, what are the roots? How many roots do you have?
2.
You still have 2 roots, but they are they different?
They're
If
the same.
it's 0, it's gonna be the same.
They're the same.
Same, and they are real. Remember 2 weeks ago? When you solve a differential equation and you have 2 roots that are real and equal, what is the form of the solution? The one I wrote
Yeah.
on the board, that
Yeah.
maybe, hopefully I wrote it there.
A1 E S1 T
Yeah.
plus A2.
It's the general one, right?
It's the general.
Yeah, that one, so the correct, it's okay. So we talked about this one here. CC is equal to this, C is equal to that. For any damped system, the damping ratio, again, this is a damping ratio is a non-dimensional number that defines, which is called zeta, by the way. Zeta, Z-E-T-A, which is simply the ratio of the damping, the actual damping divided by the critical damping.
When do you use that? Like, what is the damping ratio?
Or what's gonna come up pretty soon. Yeah, can't wait. We're gonna even do some lab on that, so. So, you know, the zeta is notation, you will probably guess why we are introducing this. I'll tell you why people write it. If you look at this previous equation, you see how ugly it looks?
Yeah.
Would you
Yeah.
rather
So you-
write it like this,
Or you just
or
put that.
would you rather write it kind of, it's a little cleaner?
What's
I
the
don't
third
think I
option?
wanna write any of those, yeah.
That's the only reason, you know, it's just a notation change. The equation looks exactly the same, okay? But we'll come back in here. If you look at case, here we're just talking about that critical damping. We're gonna come back to it in just a second, right? But really, the solution looks like, all we have determined is that now based upon zeta, which is equal to C over CC, then x of t is equal to, the general solution is C1 exponential minus zeta plus the square root of zeta squared minus 1 omega nt plus C2 exponential minus zeta plus square root of zeta squared minus 1, no minus, omega nt. Okay? Again, don't stress yourself and say, I have to remember this equation or anything like that, okay?
It's in the
That's-
book, but you have
it's
to
in the
understand
book.
how to use it.
Yeah, you have to understand how.
Yeah, but now we're gonna look at each one of those cases, okay? In other words, we have a critical damping. This is the idea. You have, for each system, there is a certain critical damping, right? We're gonna look as, what if my damping in the actual damping that exists in the system, what if it's lower than that critical damping? What if it's equal, or what if it's higher? possibilities, okay? So critical damping is only a function of what?
A ratio
Oh,
between.
critical damage.
Critical damping is only a function of the stiffness and the mass. Okay, there is a critical damping to it, right? So if I give you a mass and I give you a spring, you should be able to tell me what would be the critical damping, right? And then you can decide, so as you design the system, right? If you wanted to, for example, hit a bump and then do this, you want it to be under damped, right? If you want to just hit a bump and stop, right? Abruptly, you want to have it critically damped. But if you want it damped, but it takes a long time to go back to zero, it's like you hit it, but it dies down slowly, we call this over damped, okay? The only one that has any oscillation is the under damped case, you know, in which you can still have variations in the oscillations. So under damped means that, remember what zeta is? Is C over CC. So under damped, that means that C is less than CC, right? Which means that zeta is less than 1.
What's CC again?
Critical
the-
damping.
Oh,
Yeah.
okay, sorry.
Yeah, critical damping.
C
damping
is, C is
constant.
damping,
C is the damping.
it's what it is, and then C
And
is
critical
the-
damping is, yeah, so C.
a ratio between.
C, if you are given a system that is like this,
Uh-huh.
the damping is no, it's just C, right?
Okay,
But for any system that's written like this, you can determine what the critical damping is. Example, if I were to tell you, you have a vibrating system that looks like this, 2 x dot dot plus 3 x dot plus 5, I have no idea what this is, but hey, equal to 0. Okay? It's could be the equation of a vibrating system, right? Question number 1. What is the damping here equal to?
3.
C is equal to 3. What is the critical damping of this system?
It's,
Root 15?
Root of,
Oh, sorry, root,
it's
It's
2
2
times,
times,
2 and, or 2.
yeah, 3 times.
2 root of k times m,
Oh,
k
sorry.
times m,
10.
2 root of 10, which, so is this system under damped, you think, over damped, or critically damped?
Over damped?
I'd say over.
Well, 3 is greater than,
What's?
oh wait, I don't know, what's
This is pretty big, right? This is, I don't know
Oh,
what this is.
3 is
Point
not
32.
greater
This is like 3 point something, 6 point
Three.
something, so my C is less than.
than, so it's
That
under,
means I am?
under damped.
There you go. Okay?
I could do that on the test.
Yeah, I could do that
Now,
on the
and
test.
if I were to have this one as 17,
It's less
that
than-
system would be,
Probably less
Over.
that will be, because
than.
that's gonna be
Over.
over damped, right? But I can design it so that it will be critically damped, in which case
that
this
mean?
value better be equal to exactly this. See, as the designer, you have the control.
What does it mean when it's critically damped?
C is equal
Are we
to
not
CC.
there yet?
Oh,
Oh, I
oh,
know
we're
it's
almost
equal,
there.
okay.
We're
alright.
almost there. We're gonna see a graph that tells you how the response is
Like, what does that?
for a vibrating
To
system.
get 2 over the square root of 10, I mean 2 times square root of 10.
Yes.
Uh-huh. It's you take your.
Oh, how did we
okay?
get this, you mean?
Yeah.
Oh, because
You look at the
CC
you look at the
is equal to
coefficients.
2 times square root km.
Okay.
In this equation, what is m equal to?
2.
2,
2.
What is c equal to?
17.
What is k
K.
equal to?
5.
There you go. That's how you read those types of
Okay,
equations.
okay.
Okay?
Gotcha.
Analogies.
That was important, and I just need to get it in my head.
All right, so with that said, if it is under damped, that means you're still going to have what? There's still oscillation that is decreasing in amplitude.
It just decreases.
What makes
slower?
it decrease in amplitude, you think? Look at this, well, I keep looking at this, but it's right there. You see? This is the original amplitude, right? At equal to 0. This is the one that makes it harmonic, this is the culprit. A decaying exponential. What does a
Because
decaying
it's-
exponential do? It attenuates the thing, right? So it's almost like you have without attenuation, your thing will be like this, right? If you have an attenuation, it's probably gonna be like this. Why? Because it's being multiplied by that exponential with a negative sign on it.
So then,
Remember, negative exponential always goes down, right? So that's, again, mathematically it makes sense. You don't need to know the math behind it, but it shows a decaying exponential which multiplies a harmonic. And therefore you have what we call a, so the general solution then, even including, by the way, the initial conditions has been worked out for you. So you don't have to reinvent the wheel, okay?
So when it's
the
under
response, when
damped.
it's under damped, this is the solution, period. You know, you don't have to go from scratch. The only time you do from scratch is when you have like just a mass at the end of a spring. When you put dampers in there, I'm not expecting you to go and rederive these equations, okay? But you have to recognize which case is under damped, which case is damped, which case is critically damped, which one is over damped. That's pretty straightforward. You look at the equation, you can immediately tell, okay? So in this case then, when it's under damped, the equation that looks in general like this, but when you apply the initial conditions to it, it's gonna look like that, right? So all you have to do is figure out what omega n is. And what is omega n equal to? Square root of k over m. And x dot 0 is usually given, right? x0 is usually given. How about zeta? How are you gonna get zeta? Is that difficult to get zeta? No,
Zero.
because
Zero.
CC you can calculate based on K and M, and C you already know from the equation. So you have all the ingredients, that's what I'm saying. You have all the ingredients to figure out what is how something is going to move as a function of time, okay? Now, one thing you notice though, look at this frequency. What can you tell about this frequency? Does the system, as it's vibrating, does it vibrate at the natural frequency?
No.
Why? Because there is this darn thing in front of it. So at what frequency does it vibrate? It's whatever is multiplying t, right? What is multiplying t? It's the square root of 1 minus zeta squared times omega n. So this is the frequency of the damped vibration. Because it just happens to be that way in the solutions, you know? Because the square root of 1 minus this, it all comes out through here. I mean, we're not inventing anything.
So,
Right.
so if we were to apply that equation to
Yes.
An actual scenario,
Yes.
and we solve for x of t,
Mm-hmm.
what are we gonna get, like in terms of units and, or like, how would you
Yes.
take this and apply it to an engineering scenario?
Well, you have let's say you're applying it to a simplest possible case, a mass that is attached to the end of a spring and that has a damper on it, okay? The x would be maybe the dimension that you are measuring from the equilibrium position in
Okay.
the direction of the stuff.
Okay.
It's got an initial velocity, it's got an initial stuff. When you plug in those values, you're actually finding out how that mass is moving with respect as a function of time, okay? It could be, for example, a mass attached to the earth. So you can hit it maybe from below,
Yeah.
and then it's gonna do this,
Okay.
and then come to a stop.
So at any point, you could plug in a t.
You can plug in
it'll
a t
give you
and
the
tells you
position of.
exactly
Okay.
the position of that mass.
Okay.
It's all about the position of that. And this is kind of neat because it's an exact solution.
Right.
So at any given time, it's gonna tell you, hey, that mass is there. And because you know this position, what can you find from it? You can differentiate it to find its velocity. You can differentiate it one more time and find what is the acceleration of that mass.
Okay.
So, but one thing is, when you are vibrating, when you have damping, when you have damping, the vibration or the frequency of vibration is going to be 1 minus square root zeta squared times omega n, okay? So it's different. And is that going to be, and notice when there is no damping at all, what is the value of zeta when there is no damping, by the way? If a system does not have any damping at all, what is the value of zeta?
Zero.
Zero. Why? Because Weber zeta is C over CC, right? CC is always a characteristic of the system, right? But if there is no damping, C is equal to 0. That means that zeta is equal to 0. If you plug in zeta equal to 0, what happens to this term?
Becomes omega n, and omega d becomes omega n. Oh, sorry.
No, what happens to this term?
Becomes
Just one.
It's just 1. This term will totally disappear. It doesn't matter what t is, right? Why? Because exponential 0 is 1, right? And then what happens to the frequency of vibration? If zeta is equal to 0, omega d becomes
Omega n.
just omega n, right? And then what happens to this term here? Well, obviously, you know, there's
Same thing, cosine
many things
omega
that,
n.
well, because the solution here is
Cosine
something
one,
with
right?
t and stuff, but in any case, you got the zeta is equal to 0, so you got cosine t, but when zeta is equal to 0 here, you got just sine omega t, right? So you're essentially getting the actual solution that we got before.
So what is zeta again? Zeta is just,
Zeta is the damping,
but what's the name? Does it have a name other than zeta?
it's a
Like
damping ratio.
damping ratio.
Damping ratio, yeah. It's a ratio, it's a damping ratio. So, physically speaking, this is how the underdamped solution looks like. Always think it's underdamped, that means it's a sinusoidal or cosine that just decreases in amplitude, right? But the frequency is not omega n, but it's omega d. That's all there is to it, you know? It goes down and down and down. The lower the value of zeta, you know, the more it's going to vibrate before it comes to a stop, right? Okay, so that's the first one, that's the underdamped, that's kind of the most common one that people work with, right? But the damped frequency is obviously always, so you have this equation you will be using a lot. Omega d is equal to square root of 1 minus zeta n squared. Again, always remember that zeta is equal to 0. Zeta is equal to 0 is when you have no damping at all, okay? That's why omega d over omega n is equal to 1, and obviously when zeta is equal to 1, meaning that you have critical damping. When you have critical damping, what happens to the frequency of vibration? Comes down, goes down, goes down to 0. See? This is undamped, this is undamped, this is all underdamped, 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 underdamped. And then when you get to here, that means you have reached the critically damped. Critically damped, is there any frequency of vibration? No, because omega d is equal to 0. Okay. Critically damped, that's when zeta is equal to 1. That's what I was mentioning earlier, when you have critically, when you have this term under the radical equal to 0, you essentially have two roots which are the same and they are real, okay? We did this in the lab last week, and the solution can be written now as simply C1 plus C2t times exponential minus omega nt, if you guys remember.
So when they're same and real. It's
Yeah, when they are real and the same.
the exact same.
Yeah, exact same. That
Oh,
the
yeah, that
solution
makes
has
sense.
to take up this form, okay? And again, now it has been worked out for you. Even the initial conditions have been incorporated. So in this case, if you have a critically damped system and you know x naught, usually you have to know that, you have x naught 0, omega n, you can get it, right? So you can actually immediately write what the solution, how that thing is going to vibrate, immediately, okay? Without reinventing the wheel, okay? So anytime you talk about damping, try to use the developed stuff as much as possible. So the reason we are going through it like this, so that when you go back in your book and look at it, you go like, what the heck is this, you know? So we are looking at 3 different compartments. You know, one is the under-damped case. We are now looking at the critically damped case. Now we'll follow up with the over-damped case in just a second. And clearly, it can be seen that the motion, does this equation have any sine or cosines in it? So does that mean, does this motion ever will have any up and down? No, because there is no sine or cosine in it, okay? So we call that an aperiodic. Periodic meaning the periodicity. Aperiodic, that means there is no periodicity in it. So, and the motion clearly, because of this term here, that culprit again, exponential of negatives t, where t approaches infinity, the limit of that function goes to 0. That means that the motion will eventually diminish to 0. Last case is the overdamped case. Okay? The overdamped case is when that term in the radical is now greater than 0. So what kind of roots are you gonna get in this case? 2 roots that are real, and both of them are positive.
So wait, underdamped, are they also real?
No, underdamped is, underdamped is when this guy,
Is 0.
no,
Less
that's
than-
when it's critically damped, that it
Oh,
is 0.
right.
When it's critically damped is when this guy is less than 0.
Less, yeah, yeah.
When it's less than 0, technically you get that's when you get the imaginary thing and you have
Oh,
oscillation, right? But when this guy is greater than 0, right? Or when this guy, zeta squared minus 1 is greater than, zeta squared is greater than 1, obviously this is real, that is real, this is real, this is real, but both of these will be different. You know, it's like having minus 3 plus 4 and minus 3, let's say minus 4.
okay.
You know, so 2
So-
roots that are real and different.
Is underdamped.
No, this is
Overdamped.
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 That's overdamped.
Yeah,
You know what
overdamped.
helps is looking
Real
at
and
this
different.
diagram.
Underdamped is the only one that still has oscillations,
Okay,
okay? That's when zeta is less than 1, right? And critically damped is when zeta is equal to 1,
yeah,
and overdamped is when zeta is greater than 1.
yes,
Okay, because zeta is obviously C over CC, okay? So this is the critical, everything is compared to the critical damping. If I'm below that, no, that means I'm got a long way to go. If I just hit it right there, that's the perfect one, right? And if it's greater than 1, that means I'm overly damping the system, you know? That means it's still going to go to 0, but it's gonna take a while before it dies down.
Could you compare it to like the rebound of a shock absorber?
Exactly, yeah. When you do the rebounds, when you hit, you know, you get a cannon or something like that, you don't want that darn thing to
Right.
back and forth. You want that thing to be critically damped, or maybe slightly over damped, if any, you know, just to make sure that you don't get any residual vibration.
Okay.
Yeah. So for the overdamped case, because we have 2 roots that are real, and remember we talked about this before, it's C1 exponential root 1 times t plus exponential C2 times, plus C2 exponential root number 2 times t. And again, this problem has been worked out already in the book, right? In other words, you still have to figure out what the heck C1 is and what C2 is, and you can get those by applying the initial condition. It's a fairly lengthy process, right?
But we have to do it on the test.
not this test.
Or if
no,
you want
chapter.
to. And this one will have you obviously do the, what C1 is, what C2 is, okay? Yeah, if you get into this and something like this in the test, it becomes more of a math thing than anything else. This slide is really the neat slide, a neat slide. It summarizes the three situations, okay? Remember, when we have no damping at all, what kind of motion would you have? Just harmonic, back and forth, you see, and damped. Yeah, well, here it is, I didn't realize it was here.
Yeah.
See this solid one here?
It's solid.
Just coming in, it's undamped. Undamped means that zeta is equal to 0, okay? The next one is the underdamped. Underdamped, where you have zeta less than 1, right? So it's this one, right? So come back from there, you see what is happening? You're coming in, you're still oscillating, but what's happening between the two?
Amplitude's dropping.
The amplitude is
Getting smaller.
Diminishing.
dropping. And the other thing you should probably notice is that the period between the time, I mean I guess the period between here and here is different than the period associated with this guy,
Hmm.
okay? See, 2 pi over omega d, and this one is 2 pi over omega n.
Well, it would have to, right, to
Yes.
be able to lengthen out. the-
Exactly,
Okay.
yeah, so it kind of stretches out,
Right,
if you will.
right.
And I like the critical damp one that just goes to.
And look at the critically damped one, which is zeta equals exactly to 1. What happens? You come in, there is no, it just goes up, oof, like this, come back and just dies down very quickly, right? And then the over damped, what happens? It still dies down, but it's taking out a longer time, you know? There it is. That's all there is to it. It's like you're giving it more damping than it actually needs, right? That's why that thing's still gonna go to 0, but it's taking much more time. So these are comparisons of motion with different types of damping. Hopefully up to this point you know what the difference is between critically damped, underdamped, and overdamped. Couple more things. On the solution, it says here, the free damped response of a single degree of freedom system can be represented in the phase plane or state space as shown below. What are we showing in here, you think? We're showing a plot where we're showing the position with velocity, right? If you have a situation in which you have absolutely no, where you have what we call no damping at all, right? So you're, you know, everything is with respect to 0, you're just kind of cycling back and forth, right? With position, you're moving this way, right? Moving to the maximum x, 0, minimum x, 0, maximum x, etc., etc. And for velocity, the same thing, right? You're just jumping between up and maximum velocity and minimum velocity. What if you have an underdamped? Underdamped, you're starting from the initial position, initial velocity, and what are you going to do? Why are we going this way? Because the amplitude will be decreasing, right? Decreasing, it's almost like a little spiral towards the center, right? So you're coming in here and maybe have 1 cycle or 2 cycles, but eventually you die down, right? If you have it as critically damped, that's the shortest path to stopped without any oscillation.
When do you begin to delineate between critically damped and overdamped? Because their relative motion is the same, it's just the period of time
Yeah,
between them?
the one that takes longer, obviously, is the overdamped one.
Okay.
You know, that's the
Okay.
only thing that changes.
But in like a testing scenario?
Yes.
Is there like a general guideline to say this is critically damped or this is?
Oh, that's from the, a lot of people, when they do those things experimentally, they try to kind of move that C a little bit, because they like to capture that end part of the underdamped, right? Because you're gonna see the stuff and then you go, now I'm the critically damped, so
Okay.
this is the,
Yeah.
then they can
okay.
see it. Because
Okay.
both of them are not showing any stuff anyways.
Right,
Yeah.
right.
And it's mostly also from the calculation of the stuff too. And this is the overdamped again, which does not show any oscillation because we're not rotating in any ways, but going to the position in taking a long time longer. This concept here, again, I'm not deriving it, but it's a very important concept in dynamic, in vibration. It's called the logarithmic decrement. What is it? If you go through the book, the derivation is fairly long, and I don't want you to worry about it, but it's in any textbook in vibration, it's a very important concept. The concept is this: if you have a damped vibration, what happens to the amplitude between one cycle and another?
It gets smaller,
It
right?
gets smaller, exactly. If you work out the math, right? If you work out the math,
It
you will
fits that
find,
table.
you will find that if you have maybe between two consecutive cycles, right? Maybe in the first one you have an amplitude x1, then it goes to amplitude x2, right? If you take the log of x1 over x2, you will find what we call the logarithmic decrement. So what's the use of it, right? If you do the math, you find that it's equal to zeta times omega n times tau d, okay? Which is the period of the damped vibration. But the important thing, look at this plot right here. It shows the variation of logarithmic increment with damping, right? So you're plotting delta versus zeta. So when zeta is all the way to about 0.3, right? In other words, when zeta is really less than 1, you can figure out that delta is equal to 2 pi over zeta. I mean 2 pi times zeta, where zeta is equal to c divided by cc. Now,
So your slides,
Yeah, they're not.
Okay.
Yeah,
updated.
they don't
Doesn't
match what
match.
you posted.
You must have updated them.
yep. Probably just added borders maybe to the equation.
No.
No, the
no.
equations are different.
From 2 pi zeta over 1 pi zeta. whatever.
Yeah.
That's
Oh,
not
yeah.
there.
Yeah.
Should probably start over.
I mean,
You added some stuff.
Maybe as I was looking
Sorry.
at it, I
you
went,
don't even-
Sorry.
You don't have.
I can post the revised one.
It's the, yeah, it's the derivation of it.
Maybe it's just in the,
Just leave it off the task.
There you
well,
go.
the
We're
logarithmic
not getting-
decrement is if you have delta is equal to 2 pi zeta, where zeta is c divided by cc, okay? I'm just gonna tell you what this is really used for. If you have this, if you measure the logarithmic decrement, which is the log of x1 divided by x2, so you do an experiment, and then between two cycles, you know, one vibration and then the other one, you measure x1, you measure x2, you take the log of that, you find delta, then you say it's equal to 2 pi zeta, but 2 pi zeta is equal to 2 pi c over cc. Cc is just a function of the system itself, whatever mass you have, whatever the spring you have. Now, what people use this for is to figure out what the heck c is.
So,
So you can determine damping by an experiment just through the use of, so let's say you have a damper, you have no idea what the value of C is. So you are in a lab and you go, okay, I don't know, I know it's a damper, but I don't have its characteristic. I don't know what C value is. One way to do this is to do an experiment in which you create what we call an underdamped situation, and then you will look at how your stuff goes like this. Maybe here you have, this is x1, and then this is x2, right? Between two successive ones, right? And then from there you calculate delta, which is log of x1 divided by x2, and you know mathematically that this is equal to 2 pi c over cc, where cc is equal to, what did we say, 2 square root of km, right? So from here, I can say then that C is simply equal to Cc divided by 2 pi times delta. Okay, so just a quantity that tells you, if fact, you see here, if the damping in a system is unknown, it can be determined experimentally by measuring any two successive displacements, x1 and x2. That's the only thing the logarithmic decrement is used for.
By a system, could that mean like, just a material? Like if you had like a piece
A
of.
vibrating system.
Right, okay.
And
So
it has to be vibrating, because, you know, if it's not vibrating, you cannot measure x1 nor x2. x1 being the amplitude of that vibration at 1, and then the vibration at 2. In fact, you could use this one if it's continuous vibrating like this, you know, this could be x1 and this could be x2. As long as it's just two successive ones that
What
you
is-
can get data on.
What is delta on that graph?
It's meaningless, it's just a quantity.
Okay.
That's, so you cannot show it in, it's just a rate, it's the log of this
Okay.
divided by that.
Okay.
So, it's not something that you can show on the graph, and it's not a dimension by any means. But it's a very important thing that is done in vibration, because that's one way you can measure actually the damping of a system. Not lastly, but,
Before the test review.
because we have
Labs.
damping, obviously we're gonna be losing energy down onto it,
Yes.
right? And what causes you to lose energy is the C, you know, the damper, because if the C is equal to 0, we said that there is actually no loss of energy at all. So if you look at this case in here, in a viscously damped system, when x is equal to x sine omega dt, right? Because it's a damped system, it cannot vibrate with omega n, but it's going to vibrate with a damped frequency. The rate of change of energy with respect to time is going to be given by, so the damping is actually occurring at the damper, and we know the damper is, the force developed in the damper is proportional to the velocity. So F is equal to C times V, right? And remember what work is? Work is force times distance in general, right? That means that, I guess, power, if you will, right? Let me call this X. Power is dW over dt is equal to force times dx over dt, or in general, it's force times velocity, okay? But we already know that this force is proportional to the velocity anyways. So, in our case, because we have a damper, this becomes CV squared, right? With a negative sign, obviously. dW over dt, it's a negative sign because it has to be decreasing, because you're not adding energy to the system. So this becomes FV, which is minus CV squared, which is minus C dx over dt squared. No need to know about how this integration is performed, but once it is performed, that means you integrate here over an entire cycle, right? To figure out how much energy is dissipated in each cycle, okay? And it turns out that it's equal to pi times C times omega d times x squared, okay? Where x is the amplitude here of vibration, okay? In a viscously damped system, okay? This is the definition, which I think I'm gonna skip. Break time, you think
Yeah,
it's
let's
time?
break.
10 after 6.
Yeah.
Let's take a little break.
Yeah.
It's only 5
Yeah.
o'clock.
An hour.
2
It's only
hours.
5
Yeah,
o'clock.
It's
16, sorry,
6:10.
yeah.
We have yet to do two
Yeah,
labs.
10 after 6.
And a test review.
Yes,
Yes.
Yeah.
that's why we're getting frustrated back there.
When you do test review, and,
Yeah.
I mean, we don't have to do a lot.
These chairs are so comfortable after 2 hours.
Rain.
Did I?
And we have two labs today.
So bad.
You wanna have a note, I would frequently look at that when I sit over there.
Yeah, I'm like-
Yeah.
This room is so small.
Today class.
Try
No,
some of your
there's a
crackers.
handful of classes I'll be here.
Now that there's none left, cool. Good job, me.
I offered them to you
I
last
know.
week.
That's why I said good job, me.
Oh, I
Good
think
shit.
Scott's still recording. Should we do
That's
something
fine.
about it and let him be?
No.
Yeah, we should moon it.
Did it show up?
Yes.
Peace.
He's still recording it.
Classy Clancy.
I have trouble posting
been a bit
any video to YouTube more than 20 minutes long.
Okay.
Taking a break, so yeah, obviously.
Have
you
three
Oh
said
my
you did
gosh,
for a
that
while.
was a while ago.
How long you
What?
been back?
No.
Just finish it.
No.
A year and a half?
Okay, Mac.
I took, so I
Okay,
took
yeah. Oh my
three
God.
terms, no, 2 terms off.
Laser.
How much you got left? You're already in vibrations.
You know, 2 year return.
So it's fine.
I'll be done next year.
The darker ones,
Like,
this
like
bunch
in
has like
spring, summer?
burnt ones.
Right, you
I don't know what it is.
What flavor?
Lord,
Yeah.
You macadamia
Oh,
nuts?
What do you have left?
Just
I
plain
have,
salt.
so we'll
Burnt.
take
And they
fluids
roasted them, some
2,
of them are burnt. You
heat
see the darker ones? They're supposed to be light.
control.
Macadamia nuts are supposed to be the lighter.
I have that
kind.
second
Lighter.
electrical
Much lighter.
class.
Those are the ones that are like
Maybe.
really good.
Can we take these
And
off your hands for?
then senior project?
Darker ones are.
You got-
Let me help you with
I'm
that.
not going to the same rate you
Darker
are.
ones are
You're busted out
burnt.
and killing yourself.
I don't like the
So-
burnt ones.
This program since 2013.
You can have all the
Same.
burnt ones.
Really?
Yeah, but I didn't take a year off. I was like summer off 1 year, but.
No, they don't
I,
have
uh,
recycle.
I have, this one obviously controls next term. I have materials 2 to do, but I didn't do materials 1 except for 20 years ago, so I'm gonna take them both.
Oh, really?
Yeah.
I actually really liked materials. Oh wait, strength materials?
Not strength of materials,
Or,
I like that one, because Dr. Bridges also, but this is the one with memorization. It's just called materials. It's like a chemistry type thing, I guess.
Right now?
You must have prerequisites for it or something?
I told you I just about didn't come in.
This
How
is
many
in
classes
one
do
of
you-
those days.
I 6 or something, so I got controls.
Yes, please.
Senior projects, all 3 of them.
Mm,
Materials 2, but that means we got 1 and 2. so I'm not
You
gonna
locked
do
in.
without 1.
mm.
And I think just chemistry 2. So just the chemistry 1.
Oh.
Like I got an A for the class, but a B in the lab, and it was my only B, and I was like, and it was just like, I don't know if you had to take chemistry, so you had the prerequisites for it, but she made, you know, she really like your chemist.
Yeah. Oh, I didn't take it with that new lady. I took it a while ago.
Yeah. How did you find it? Not too bad, huh?
I mean, yeah, I struggled, but not like, yeah, I don't think it was as bad as everyone else
Well,
said.
I just say it was a friggin' lab. Give me a break, dude. So I just didn't take chemistry because I demoralized. I'm gonna take it without remembering it.
We got
I guess it's possible that you didn't get the chemistry.
Who was your teacher?
Some guy.
His name, yeah.
At
North
North
Seattle.
Oh,
They used to
right.
do all I
Was
should
he-
know.
It was
Oh, you did.
And we only
Was it
have
pretty
2 chemistries, not 3.
No, I like take 2 as well.
Yeah. Because they're making a lot of people take 3 now.
It was a
Oh,
little
yeah, that
bit,
intro, that's right.
it was a little bit hard for me.
Huh?
Can we talk about chemistry?
Yeah.
Yeah, I had to take it. I didn't enter when I first started this program. I waited long enough, and sure enough, I had to take it.
Yeah.
Well, it's like I only had to do 3 electives, now you gotta do 4.
What?
Oh, really?
No, you don't.
Well, after you, if you start the program now.
Oh,
Yeah.
okay, okay.
You're
okay.
grandfathered in your catalog.
Yeah, we're
Oh, we only have to do 3?
Oh,
I think so.
I thought we had
Four.
Better
I
not
started
take a
in
break.
2014.
Yeah, I
You're
started
not taking a
2013,
I said,
so.
better not take a break. I'm gonna get
you.
this shizzle on, dude.
Really? Because I think I keep
Shizzle
updating
on
my
it,
thing
no
to
whistle.
the curriculum that's out now. So
Why?
hopefully, I don't know.
It
I might
shouldn't.
drive me to quit. Just one more.
Hopefully
One more to
it's
do
just
it.
the 3.
No, you're not.
I'm gonna have to talk to Mark.
You're not gonna, because I,
Yeah.
sometimes I really
Wait, what?
felt
Cynthia, like, if anybody quits, I'm gonna.
So-
I like those are dope.
How come we're doing control systems next term instead of just waiting to do 2 classes at a time? Because you're taking 3 next term? Yeah, but control systems. Because when Marcus was talking to me, he was saying, okay, take fluids 2 and heat transfer 1, and then take, because you have to start senior projects, so you're gonna be in this, going in the spring anyway, take control systems then.
No,
No?
I don't trust
Just-
anything he says.
Okay. Well, perfect.
I can't.
Okay.
The number, the other crap that's while we're doing.
If I were younger, I might get more money,
That's-
but I think it's
No.
gonna get me higher, so it is.
Because we're
more
gonna
money,
spend,
because
be
I
spending
don't
spring
want to-
quarter,
zero.
all
Yeah.
spring quarter finishing.
Or 600 a month for the,
Because
whatever.
it's
Okay.
crunch time.
Six
Yeah.
hundred a month,
Alright.
1,200 for the unemployment.
Then
Yeah.
that's good to
Whatever
know.
it is.
That's kinda
Unless you're
cool.
Scott, and then you just get it done in 1 quarter.
At least
What?
not initially, I
Senior
think it wears
project.
out after a year or so, isn't it?
I worked ahead during the summer.
That's
I had
awesome.
nothing to do. I had no classes I could take.
You have-
The only reason I'm
I've
doing it is,
never
like, if I get
had
laid off, I can
nothing
get a job
to
that's
do.
paid enough.
Yeah, it was
Right
weird.
now,
Last
I'm not
last
taking
summer I
it.
couldn't take
Did
any
you
classes.
just not know what to do with yourself?
Well, I didn't want to waste it because I knew
That's
it's
true.
this quarter
Yeah.
and then next
I
quarter
have
for me
to.
to
Be
make
rough.
credit.
Yeah.
Otherwise,
So I spent like
And I kinda don't like it, 'cause I like where I
200
am, but.
like I worked
Nothing's
because I kind of had nothing better to do, so I just kind of
Right, yeah, focus
obsessed
and
on
got
it a
it
little
done.
bit. But
That's so nice.
so I worked ahead.
Holy cow, I wish that's
He's
awesome.
a mystical engineer.
Each their
I
own.
thought about going either into ME or.
Which is the
How do I
easier,
know?
Yeah.
imaginary engineering?
Imaginary.
That's way easy.
Maybe it was like catcher.
You don't need an engineering degree to get it.
Yeah, you know, that's why it's called imaginary, I guess.
You're not really an engineer.
Yes, I am. Yeah. I got a friend at IE, and she's awesome. so
Yeah,
that's
I
not
did,
actually that
yeah.
bad.
Okay.
I feel like you're not gonna bomb a test
Well,
though.
I've never felt like I'm gonna bomb a test more than
Yeah, I know.
I do right now.
Oh, this is my constant feeling in life now. And his class last term in dynamics, I had waited so long to take it after taking statics that I just had it was bad. It's the first C I've ever got in my entire life. But he like gave he came up with some weird like equation and gave people extra.
I thought you were.
And he'll give you a chance so you don't get a
Have you always
D
been
in class, you know.
Yeah. I don't even care. I mean, a D is done, right?
Yeah,
You pay the
it's
money
done,
back,
but I don't
you're
wanna
done.
pay it.
Yeah, I want to
That's
pay it.
I think it's very rare. You'd have to like not show up and not turn anything in for him to.
Yeah, I just
Right.
didn't come in. It's like,
Okay.
So you can be a manager.
That's what I mean, I could be a
Yeah, this is
manager.
stressing me out. This
Yeah,
is
this
like-
I fucking hate the book, and I
Yeah.
not.
But I mean, that
Plus, I
you
stopped
were-
listening like at least 20 minutes ago.
Yeah.
At least.
Better people than me, I
Yeah,
can't be a manager.
thank you. I'm gonna put those out, put them with my
No matter
notes.
what you do, everyone hates the crap out of you.
You're in a shitty.
Yeah, I'm impressed.
That's literally what I
You
already
gotta
have.
do all that.
He said he was gonna do a
How
good
did you know
test
so I
review,
didn't?
and I'm really hoping he does
You gotta
because
do,
based on the
annual
homework,
budget stuff.
and we
You
have
gotta
2
do,
labs, so. Which is why I was like, why haven't we stopped already? It's supposed to be 2 hours lecture, right? It's a 3-credit class.
Well, yeah, it's a 3-unit class. That's true.
So why do we have
I was writing it down. As long as it's still recorded.
That's why we did it. You'll hear the lull.
You'll hear all kinds of
You'll
things
hear us
on
all
there.
going, oh, it's still recording, should we do something
pretty
about
good?
it?
Please do not stop recording.
But what you should do though,
Guys, we nuts. I'll be halfway through a class.
And then just
My dad will
what I hear anyway, what
And
you
it'll
should
stop
do
the
is that
video.
you,
I have to put it in airplane mode now.
is that you,
I get some random call. Like, dang it,
Become a manager.
2
That happened to me,
seconds.
yeah. 'Cause I saw you videoing machine design,
Stays the same,
and
but-
I got a call, and I thought it was still recording, and it
I know a lot of people who did that.
It should give you an option, like decline and keep recording.
And then went back to being
Yeah.
engineers.
Yeah.
Yeah,
Why
I
not?
know a lot of them.
He went from second level down to second analyst.
Well, you know, like,
But his
when
mind
I-
stayed the same, and who gives a
When
crap,
I
right?
started going 9 years ago, I came from Logan, I was a
I
director.
get confused.
So I took a $35,000, never mind the benefits, stock plan, all that.
I feel like, yeah, 'cause
I
I'm
took a
doing
$35,000 a year cut
But he said
to come to work
one
for Bob.
problem.
But it was the only job I could find, and I was really glad to have it.
He had,
So I was like,
handouts up there.
35K,
yes.
it's not insignificant.
And after 9 years, I haven't made that back yet. That shows you how small the raises are.
Do you remember Tin, Tyler?
What?
Tin.
I'm asking you, I'm assuming you have.
He's freaking awesome, dude. He got like what?
hear he does.
He got a 30K raise when he graduated, right?
We should have
He's the
fun.
guy who was like
What?
the absolute expert at having people do stuff for him.
Yeah, yeah.
And he
You
comes
have.
to a test.
Do you think the lab is gonna be like a
really
group
tiny.
effort,
He
like
was-
fluids?
No, no, no.
Or we just do it once?
Yeah, he was
Cause
hilarious.
I
He
don't
came
have
with like
the
30
brain.
solutions shrunk
Well, it
down.
seemed like.
So he
And
could
eight
do
out
like
of the
the
10 were on
whole
there, so
class
he got 8
example
out of
and
10
you're gonna
because
write
he
the
was
lab.
freaking
That's
clueless
fine.
all the
I
others,
mean,
right?
that sounds like it, out of my individual.
I just don't wanna go set up,
with
like,
it.
everyone has to set up their own
I
shit.
know.
and-
Okay, thank you.
Drip, drip.
Yeah, he was awesome.
God,
Free
that's annoying.
vibration of a
I
single
think for
degree.
machine design, you had an
freedom
engineer friend in
system.
California do
Single
the
degree of
midterm for him.
That's
Yeah.
what
I hope we don't have homework this week.
No.
That's a classic.
Well, we're not gonna finish chapter
We're only
2.
doing, yeah.
Machine design?
But there's
Got
still,
up to 2.11.
I think there's still 40 more slides.
Project and stuff and having to go and just.
Mostly.
These chapters are
We'll have a
so
little bit
long.
of chapter.
I was
Work
there.
is all
He
right.
said he's gonna
That class
spend
for sure.
45 minutes to read.
Are we gonna review now?
Yes, let's do
I don't think I can do any new
No,
information.
he said he's gonna write something on the board and you guys are gonna go.
I don't know.
You're
The wells
expert
run
of these.
dry.
Yes.
But don't let Kathy go until he might write stuff that. Honcho fraction shit.
Taki, you want there?
Sound
So,
effects.
if we don't do so well, can we retake it?
Retake?
No.
What do you mean retake?
Get it
I
next
would get
time.
very angry.
We can pass with a D though, right?
You just get the grade
for
for
it.
it.
Pay for it at the D though. That's
Oh,
still
it's true.
passing.
That's still passing.
I don't care at this point.
I mean, I'm not personally gonna.
You
Set the
drive
bar
for
pretty
that,
high.
you
But
can get
it's passing.
Do you feel confident that you can get it?
Nice strong.
Oh, God.
We got this.
You got this.
Said with such
Thanks.
confidence. Someone's got this.
Not
We
it.
got this?
Why did they make us take this class?
Torturous. What did Dr. Mead say? You're gonna use about 15% of what they teach you, but they don't know which 15, so they give it all to
I know which 15 I won't be.
Yeah.
Probably just don't have to.
Which 85?
Dr.
What did Dr. Mead call Dr. Abbott? Yeah, he didn't abuse.
I
was like, hey, my bad. He was a good sport.
I mean, well,
For you,
it came
sir.
from you, first of all. So of course he was.
I really didn't.
Don't use the other one.
If you have an inclined plane like this, an angle theta like here, you got a little mass M. You got a little spring K here. The question is, first of all, what do you find equation of motion? Find natural frequency. And then third, what effect does gravity have, if any?
Can you just say none?
Well, you gotta show how.
And say why.
remember, this is just an idea before. We talked about initially about this, right? K and N, that's how we started with this whole thing, right? And we came up with that equation, mx dot dot plus kx equal to 0. And then if you recall, we also looked at it and said, what if the spring was hanging, right?
Yeah.
Because now you got, here the gravity is inconsequential because, you know, there's a normal force that cancels out. But what happened in here, did we get a different equation here,
No.
or was it the same? But the spring is elongated though.
It was just a different equilibrium.
Yeah, thank you, it's just a different equilibrium position, but we did the math behind it, right? And then we found out that mx dot dot plus kx is equal to 0, right? So, same equation, same kind of idea here. So how do you find the equation of one?
Mx dot dot plus kx. Free body diagram.
Yeah, that's what you want, a free-body diagram and do it the classic way, you know? So I'll give you a couple of minutes, 5 minutes, 10 minutes. I thought Clancy volunteered, but I think, you know. No. Nice. Go and solve it. Okay. Tough one?
Hmm?
Tough one? Tough
I
one?
mean-
I'm having to go back and look at everything.
Well, let's try to do this together. When this mass is attached at the end of the spring and it's in equilibrium, right? What are the forces acting on this? Okay, this is at equilibrium, right? That means I have a plane like this, right? My mass is like this. How many forces are acting on? By the way, this is frictionless, obviously, right? I may not have said this, but you know that.
How big?
Yeah, that's the only thing I was holding you
I
up.
was holding you back.
Oh, now you tell.
So you.
Two forces.
It's just sliding easily,
So we
right?
got gravity.
So we got gravity,
MG
okay,
and KX.
In the spring.
mg, okay, and you have what?
KX.
K,
Well,
K delta static or something like that, because it's,
Unless we define X as a long.
because my x is starting from here. We haven't started moving the thing from equilibrium yet.
At equilibrium.
Okay, but here at equilibrium, you know, as the block is sitting here on this, the spring has to be stretched
Right.
somewhat. Okay, now what is this angle here? It's obviously theta, right? And this angle is theta. So what equation can I get from here? And obviously there is also another force, by the way, you guys didn't tell me.
Normal.
Force.
The normal force.
we did say that.
Okay, thank you.
Perpendicular.
Clancy
Yeah.
said that.
So on the plane side, I guess, or on the incline, the sum of the forces is equal to,
Is that equilibrium?
And that's not.
Some of the forces equal zero.
no, it
Because
should
it's
be
like-
zero,
like
because it's an
zero.
equilibrium. You know,
Equilibrium.
just as I'm looking at this guy,
Uh-huh.
it's not moving, right? So what is this for? What is the component of mg in this direction?
MG sine theta.
Cosine. Oh, sine theta.
mg sine theta, right, in this direction. This is theta.
Yeah.
We good?
Yep.
Okay, mg sine theta better be equal to, well, or minus k delta st, right? Is equal to zero. Meaning that k delta st is equal to mg sine theta.
Mhm.
Okay? Now, we're gonna start the vibration. I'm gonna pull my mass,
The equation of motion.
I'm gonna pull my mass the distance x, okay? So I'm gonna have now free body diagram again. As I pull my mass at direction x through here, right? How many forces are acting on it again?
Same.
Same two.
Same.
too.
Same. So we're still gonna have weight, mg. I'm still going to have the
Normal.
a normal force, but how about this force now? What is it equal to?
KX.
It'll
K,
be K times delta static plus X. Okay, X plus delta static.
X plus delta static. I mean, it's already stretched delta static,
Right.
and I'm pulling it an extra X. So it's gonna be K times delta statics plus X. If you don't agree with this, please let me know. If it's ambiguous or something like this. The spring here is already stretched delta ST.
Right.
And I'm pulling it to the right
An
by
additional
X. That means the total stretch now is K delta ST plus that. Now, what is the sum of the forces in the X, in this X direction now? Equal to? Is it 0?
No.
No.
MX
Because
dot
now
dot.
it's moving, you
Yeah.
see? So, what is the component of this force now in that direction? Just like before, right?
MG sine it.
mg sine theta. Obviously, I have to subtract that
Subtract.
force minus k delta st plus x is equal mg sine theta minus k delta st plus x equals
MX
dot
dot
dot.
dot.
mx dot dot. Okay, now I expand this guy,
Right.
mg sine theta minus k delta st minus kx equal to mx dot dot. What do you notice in here?
K delta
Oh, they're the
ST and
same.
MG.
Yeah, so what happens to this term?
The zero goes away.
What do I end up with now? Minus kx equals mx dot dot, which means mx dot dot plus kx equals to
Zero.
0. So what is the natural frequency of my system?
Square root of 1
Was it
over
K?
1.
Square root k over n.
Oh, right, K over n.
Then, is the gravity having an effect in here?
Nope.
No. So just like we had the mass sliding on a frictionless horizontal surface, we looked last week or 2 weeks ago when we had it vertical, it kind of makes sense that in between it has to be kind of
Yeah.
the same. So
So
we have just shown
at
it.
this point in the test, we would say we have shown that gravity doesn't have any effect.
Absolutely, yes. So gravity, because none of
It's the
this,
same
you
equation,
don't
so-
have gravity in this equation. If gravity was in the equation, that means it would have an effect,
Okay.
right?
And you were able to take out MG sine theta minus at 0 because
Of the initial
We already-
condition.
Because of the initial
initial
condition.
condition. Ah,
It's balanced, you see?
ah.
You know, that's the key thing. That's the same thing we did for the analysis of the previous one.
So we're saying that gravity doesn't have an effect on the vibrating system,
Yes,
but gravity does have an effect on the static system, right?
definitely,
Okay,
yes,
okay.
yeah. Because what the gravity has an effect on, just to be more exact, is the shifting of the equilibrium position.
Right. Okay.
Yeah,
So basically, since it's acting constantly,
yeah,
it doesn't make any difference.
yeah. So you're just shifting, so you're taking that part out. Remember that block that we threw in? You know, it's the same thing. You're just shifting the position. Because if theta is equal to 0, what's gonna happen to the spring? If suddenly we bring that theta equal to 0, the spring will
Will be back
Oh,
to
okay.
equilibrium, right?
will go back to its
natural
natural
state.
state, right? Right? So the more you turn it, right, the more it shifts down, right? Until you go vertical, right, then it shifts the most. But the vibration, the key thing is that the vibration is really not affected. Are we good with this one?
Yes.
If you're ambiguous, please let me know.
This is possibly similar to an exam
Could be.
situation.
Yeah. So.
It's definitely good practice.
It's, yeah, well, we're doing,
So you want to start at equilibrium and then, because the initial question you asked, we didn't say that it was being pulled a distance X
You
or
said, what is the
moving.
equation of motion?
I said find the equation of motion.
So you have to just assume
Right.
that's being, yeah.
So the equation of motion is always with respect to an equilibrium position. That's why we had that equilibrium position established, you
Okay.
know?
So we're saying the standard method for such a problem would be to take no acceleration, in other words, equilibrium, to the
Yes.
sum of the forces, and then you pull a distance, and then
That's when you start, because that's when you are doing the dynamics.
Yes.
In the first one, you're just doing
it's like
the
static and
statics.
dynamic.
Yes.
Okay.
All right, now, imagine you have a wall like this. You have a mass in here. Another spring there. What else? This is a mass M, and this is, K1, maybe. And this is K2. Right? It's pretty clear what we are showing there. The question is, what is find the natural frequency of the system.
That one's a pretty quick one.
That one, in series,
Because it would be root K over M, and you just take the quick K equivalent, and that would be it.
I don't know.
Wait, say that again? You just do root K over M, that would be the equivalent?
Well, he said the natural frequency, which is root K over M, right?
Mm-hmm.
But you'd have to find K equivalent in series, so it's K1 plus K2.
Right.
Is that right? Doc's got a very poker face on right now, that's why I did that.
So what is the answer for the first one?
I think root K1 plus K2 over M.
Mm-hmm.
I screwed up the math on the second one.
Wait,
so-
what is it? Say it again?
The root K1 plus K2, root of K1 plus K2 over M. Now, let me ask you a question. The first two springs, in the first situation, are the springs in series or in parallel?
They're in
Series.
series. They're not because they're on either side.
They're not in.
Oh, because they're not.
Remember what springs in series
Oh,
are.
wait.
One is the end of the other, you know,
That's
so if
right.
they,
Oh, yeah, so
you know,
they're just.
if you
So if there's
have mass
something
on
in
one
between.
side, it does the same thing, but this one is.
Oh, shoot.
So,
But it's still the same answer.
You
though.
think it's,
it's fighting it and it's fighting both.
it's almost like, you know, in electricity, it's almost like this is the ground, if you will, right? So you're attaching from the mass, you're going to the ground and you're going to the ground, right? So it's almost like having those two kind of,
In series with the mass.
yeah, in series with the mass, but you cannot say that K, it's not gonna be softer. Spring. It would have been in series if you had this.
That's right.
You know?
So how did you?
These are two
figure that
things
out?
in series. So let's figure this out a little bit. If you look at this mass M, and you were to do, for example, this is, let's say this is the equilibrium position, everything is fine, right? Let's say I wanna pull this guy in this direction, the distance x, right? Again, the thing that will always give you the right answer is if you do the equation of motion. That's period, you know? And that's the ultimate stuff. You don't make any guesses, right? If I draw the free body diagram of M on the first one, right? What are the forces acting in this x direction? Once I pull it to the right, right? What is K2 going to be doing?
K2 is gonna be pushing that.
Pushing it that way.
Pushing this way. How about this guy will be in,
Same direction.
okay,
Pull it.
will be in tension, so it will try to push it, pull it in this direction, right? So this is going to be equal to K1, right? K2,
That's K2.
K2x, right? And this one is K1x. And this is M. My x is kind of going this way, right? So my equation will be what? Sum of the forces, which is minus K1x minus K2x is equal to,
0.
why would it be 0?
Oh, sorry. MX dot dot.
Mx dot dot, right? Mx dot dot. Now I factor the x, it will be minus K1 plus K2 times x equals to Mx dot dot. And therefore, Mx dot dot, remember you always try to write the equation as something Mx dot dot plus Kx equal to, here it will be plus K1 plus K2 times x equal to 0. Now this is a no-brainer. What is omega n?
K1 plus K2.
Square root of whatever is in here, K1 plus K2 divided by
Whatever's in front of the x dot.
whatever is on first.
So I did it completely wrong, but I got the right answer. That's scary. In
Well,
other words, I said, okay, the
So you-
equivalent spring force there is K1 plus K2, therefore,
but you said they were in series.
I know.
Remember the laws in
Series.
series is not
Oh, that's
K1
right,
plus K2.
parallel.
So you made double mistakes that.
But you
They-
still
they
got
can't
it
cancel
right.
each other out.
Yeah, that's what happened. That's why I was going like, he said series, how did you say K1 plus
Ah.
K2?
That's right, okay.
So that's
So
what
I could have
happened.
just said it's in parallel, therefore the equivalent is K1 plus
Exactly,
K2. Okay.
exactly. Now you could here, really, it's almost equivalent to having the mass under these two effects in here, right? K1 and K2, right? Because both of them are going from the mass to the ground, the mass to the ground. These are in parallel, so this is equivalent to, remember, K1 plus K2, right? And with an M, right, at the
Uh-huh.
end of it. So it's a no-brainer for this one. So two ways of looking at it.
No
Yeah.
That's why I got it right.
No.
Two wrongs do equal.
No, I would have been in trouble grading that stuff, you know, that's totally wrong. Remember, it's not the final answer, it's
Yeah,
real
yeah.
bullshit.
Yeah.
-2. So how about the other one now that we know
So
about
it's
what's
just
going
gonna
on?
be
So
K1
the
plus
other one
These
is
are
the
just
same
written in
thing?
parallel.
K1 plus K2 plus K3,
It's
you
gonna be
think?
K equivalent, right?
Because they're all in parallel.
Because they are all in parallel, see? It looks kind of, a lot of people would go like, oh, these two are in parallel,
This one is-
then this is in series, then you make it more complicated
Yeah,
than anything
so
else.
it's the exact same.
So this one will be omega n is equal to K1 plus K2 plus K3 divided by m. Now, if you were to do the free body diagram again, just to be more exact,
Yeah.
this is my mass m, right? As I push it to the right, what is K3 going to do? Compressive, so it tends to push it this way, right?
Mhm.
And we call this K3 times x. And these two will be elongated in tension, so they'll try to, hey, pull back the mass in this direction.
And because they're in parallel, you can just.
Yeah. So we call
Parallel
this
means
K1x and this one
They're
will
acting in
be-
the same direction.
Everything's in the same
Yeah,
direction.
so all of them are in the same direction, so what am I gonna have? Sum of the forces minus K1x minus K2x minus K3x equal to MA, which is mass times
Yeah.
acceleration. Right here, the same thing, you know, you factor minus x, K1 plus K2 plus K3 equal to m dot xx. Now you write it in this form, mx dot dot plus K1 plus K2 plus K3 times x is equal to 0. And from here, remember, the frequency is whatever multiplies x square root of that divided by n.
Yeah. I'm glad we're doing this.
So,
I know, I
so,
missed, yeah.
These are trick questions.
Yeah.
They are trick questions. Every single one is a trick
This
question.
is the contest we won.
So, and so don't feel bad because this mistake, a lot of people make it, even people who have,
Not Chris.
I'm not special.
you know, particularly the mass that has two springs that are attached to the thing, a lot of people think, oh, it's in series. They just
Yeah.
immediately go, and they are not in series, you know, they're in parallel.
So it's true that springs that go in the same direction,
Act in the same.
based on the force, are in essence parallel?
Well, now there are two situations here. If the springs are only attached to the mass,
Oh, good point.
But if there's
You know?
something else.
Because if
Then-
there's two springs in series, they're both polar.
because now here we are having on both sides, you know, one is going in compression, the other one is going in tension. So the final answer is really just, you know, if you think that it's gonna be more, it's gonna be stiffer, it's more likely that they are in parallel, right? But the way I like to look at it from way back when is I always go like, I don't really care how it is, particularly when I'm given problems like these. This point 4B is the same thing as this point, you know, it's just the ground and the other end is attached to the mass, so both of those will be fighting.
Right.
Both of them will be fighting the motion. If both of them were on the same side without anything connected here, they will elongate the same way and shorten the same way. But if you put one on either side, then one has to go one way. The final answer comes in usually from the free body diagram and the equation of motion. So if you practice doing the equations of motions, those usually help. Now, I assume that you guys have been working on the homework, first homework, right? So you've looked at the problem of the old drum floating in the seawater and that kind of good stuff.
Which one again?
Go back and do that
The
one.
third, I think, the third.
Oil
You know, the
That's
old
what-
drum problem, you know, whenever you put in something again, you know,
And then
that's
that
the
number,
Rayleigh's equation.
problem 22.
Yeah, problem 22. And then find equivalent spring, those are pretty easy problems. Equivalent spring.
Sounds like they're perfect for a test, huh?
Let me just throw in something here for, something that includes a little bit of damping in here, but it's.
Wait, I thought we weren't doing damping.
We'll see, I mean, we just finished the lesson.
But I thought it was only on chapter 1.
No.
Chapter 1 is like 99 pages.
99 pages, but it's got no.
There's parallel
You want
dampers
Fourier
in
series
chapter
in
one.
there?
No.
You don't want Fourier series, you don't want.
No.
No.
Yeah, you
Well,
want
we'll take some
Laplace
Laplace
stuff, you don't
transform.
want, you know. We don't wanna go there, right?
No, that's okay.
So, but one thing that you may need to, you may probably be asked to do is to get, for example, an equation of motion, because that's really all we did in the first chapter, by using the energy method. What does it mean? Well, it means you express the kinetic energy, express the potential energy, sum them up, and then just take the derivative of that, and then whatever equation you get is the equation of motion. Okay?
Say that one more time?
Yeah, or it's almost like what we did earlier with,
Isn't that the Rayleigh?
not the what's kind of semi-Rayleigh. It's not, because Rayleigh does not give you the equation of motion, by the way. Rayleigh only gives you the, like when we did the mass at the end.
Frequency, right?
Well, when we did this, K, M, right? And then we said for the equilibrium position, we said that potential energy is what?
1/2 squared.
And then we said that the kinetic energy is 1/2 of
MV squared. And then
mv
dot, dot.
squared, and then we said that the energy is this, we did this in the beginning, right?
Yes.
And then here we do d over dt equal to 0 because there is no damping in here. And then it's how we take the derivative of this, right? Remember, chain rule. Are these, by the way, I keep asking this, is this an explicit function of time? Explicit, what do I
No.
mean when I say, by the way, explicit function of time? That means, do you see t
No.
anywhere in here? But,
But isn't
but
t
these are
part
functions
of-
of t.
Yeah, it's
So that's where the
within
chain rule comes in. So anytime you wanna take the derivative d with respect to t, for this term, for example, it is an explicit function of what? Of x dot. So you first take the derivative with respect to x dot, then obviously then you have to take the derivative of x dot with respect to t. See, when you think about this, this is d over dt. That's what the chain rule is. When you want to do it for this term in here, d over dt for the, what is this an explicit function of? It's x, right? So you first start with x, d over dx. Once you are completed, then you multiply by dx over dt, because, so you can end up with the derivative of that, okay? So that's kind of the rule that you need to be following, you know, in order to solve those types of equations. Another thing that you will be obviously be given some really you're gonna be maybe told you have a vibrating system that has to take the form of x of t, right? Equals maybe a times sine omega n t minus phi, right? Maybe you will be given a mass equal to something, right? And k equal to something. Well, what the heck, let's do a number here. Mass equals 5 kilograms, right? K is equal to maybe 100. What is the unit of K, by the way? Newtons per meter. Of course, these numbers are stupid, but it's okay.
That's what I thought.
We like
You know,
stupid
we're
numbers.
just doing some stuff. So based on this, I'm gonna tell you maybe if you have an initial condition of x zero, I think we did something already before, is equal to 1 meter or 0.1 meters, and x dot zero, you guys don't like the zero, so we're gonna put 0.5, well,
I don't mind
1 meter per second.
We don't like zero?
Because you didn't just like those infinity things.
Yeah.
Oh, yeah, yeah, I don't like that.
What's the first
Right.
one?
It's a 0.1
Oh, 0.1.
0.1?
meters.
Okay, so based on this, you know, what is, for example, the natural frequency, right? What is x of t exactly, right? What is x dot of t exactly? What is x dot dot of t exactly, right? What is V max equal to, what is A max equal to, for instance. Now, when you do something like this, you don't even have to refer to the book, because you're not gonna find something there. Now you're working locally with a function, right? So, don't try to look at the book to find if it's plus phi, minus phi, or something like that. It's just an exercise that you have to go to, right? It has only a mass and a spring, so
So you can write the equation.
you should be able to find, first of all, what is omega n?
Point
Square
zero,
root.
0.2236?
I don't know,
Wait,
I have no
what?
idea.
What's
But
over
it's
square
square root
of
of
5 over
k.
100.
Square root of k over n.
Or 100 over 5, sorry.
Yeah, you did the opposite. It's too low. Square root of k over m.
That's right.
Okay, so it's square root of 20, right?
It's 4.4
Whatever that
something.
number is. And then, how do you find x of t?
You have to do it.
Please sign and make it.
The initial conditions.
Initial conditions, so you need to apply the initial conditions, you need to practice how to apply the initial conditions. I mean, it's a must, you know? We've done it, I think, so many times. Unless you want me to go through it again one more time. Or
Sure.
somebody wants to do it, I got sick and tired of it, right?
Oh, thanks, Sophie.
What does it mean?
The time to start on our labs.
Pretty quickly, yeah, 5 minutes or so, check something. Well, you know, just to review as much as you can.
So what's available to us on test? So it's open book. Can we use your
And then 3.5 by 11.
printout?
Am I ready now?
Yeah, you-
Count is from the book,
They're
so
better
that's
than
not,
They're better than, yeah. It's more concise.
you know, so you can use that if you want, yeah.
And no page?
You can have a note page.
I'm gonna have to do
So-
some of this, so I can remind myself I don't have it.
How many questions do we think?
I have, to be honest with you, I have no idea.
One.
That's.
One,
Four or
oh,
five,
one is
no.
gonna be dangerous.
No.
Yeah, you got one.
One is, we gotta spread the risk, you know?
Yeah, yeah.
You know, just like investing, you know?
Yeah, Sophie, we don't want one. True false.
All right, so I guess that's, you know, all I can say. But before we do that, by the way, I just wanna throw in something, just to see if we've got whatever we got done today.
Wait, we're reviewing what we did today?
Just a question about that. If you have a a vibrating system that has a mass of 1 kilogram, right? A damping of C equals 2. By the way, what is the unit of damping?
Well, you know that
If I-
CV has to equal F,
CV has to equal to
newtons,
newtons,
and V is meters per second, so
meters per
it's a
second.
newton second per meter.
So C equals Newton second per meter, okay? But Newton is
Kilogram meter per second.
kilogram meter per second squared times second per meter. So the meter goes out, the second, so kilograms per second.
Uh-huh.
Okay.
Yikes.
I like the way, you thought about how to get the unit. Just by going, oh, F is equal to CV, always look at an equation that involves that thing, okay? That means that the unit of C will be the unit of force, which is Newton, divided by the unit of velocity. That's the starting point. Then after that, because Newton is not a primary unit, right? So we have to relate it back to the MKS, and therefore 2 kilograms per second. And what's the last one? Is K. K is, let's say 10 newtons per meter. Okay? So what is the question here is, what is zeta equal to? And what is the natural frequency equal to? And is system underdamped, critically damped, or overdamped? And in fact, let me throw in another question, just on my own here. If this system is vibrating, what is the equation of motion? That's going to be our last exercise.
Exercise meaning this could be on the test, or this is
Not
reviewing today.
necessarily on the test, no.
That's when we're
I
doing.
mean, not necessarily.
No, it's not going to be on the test.
Okay.
But then why are we wasting time?
Oh, you call that a waste?
Oh, Chris, how dare you?
It is today.
We have limited capacity
How
right now.
insensitive.
Let's go over this next
I hit a
week.
wall about an hour ago.
Why am I always the one that sits when people are
So
thinking
that,
gets in trouble
that
for it?
won't be on the test. Just
Not gonna
leave
be
it
on the
there.
test.
Okay.
So wouldn't the,
So,
But it's good to review.
so what is the, let's start with this one.
is it mx dot dot plus cx dot plus kx?
You see, it's not the end of the world, so let's replace the thing. So M is 1.
One.
So it's x dot dot plus C,
C.
x dot, which means that plus 2x dot plus
Okay.
10x equal to 0. See, you already answered this.
Maybe this should be on the test.
Yeah.
Now you blew
Bonus
it.
question.
Now
That's it.
you want it.
Bonus
Is it?
question.
What is omega n based on this?
Root 10?
Square root 10. There you go, done. What is critical damping equal to?
Well, it's C over CV, so.
No, that's zeta.
That's
zeta.
But CC is 2 square root of
Km.
Km, of course you get it directly from there. So what is that? 2 times square root of K times M, which is 10, right? Whatever the heck this value is. And what is zeta? C over CC, which is, C is 2 over 2 square root of 10.
So it's 1 over square root of 10.
So it's
So,
underdamped.
which is 1 over square root of 10. Remember, the
10
only thing
over
we need to
10.
find out is it less than 1 or greater than 1.
So it's
Plus
This
1.
is less than 1, that means it is
underdamped.
done. You
Well,
get
you
a
can
whole
put this on the
exercise.
That's a good one.
That's a good one for the test.
But you guys don't want this.
No, Chris does not speak for
I did
everybody.
not say I didn't want it, I just said why are we wasting time if it's not on the test, but if it's on the test, great.
How long did it take?
It took about.
You-
You was like
you-
10
You
minutes.
know,
Wow.
But we learned it 10 minutes ago, though.
And if I don't have
Sure.
time,
Yeah.
I might be able to do it by next week.
Alright, so replace that with some energy problem.
Thanks, Doc, for going over that stuff with us. Very helpful.
Well, you know,
It is helpful to-
it's all about practice and stuff. I mean,
Yeah.
you don't become a vibration expert or something like that, like